Ever, that stream button, don't touch it. I've just sent you the links for the YouTube as well. Oh, right. One, two, 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 two. 1, 2, 2, 2. I'll find some. I will find some. Is that for both? Is that on the same? Is that on the same? Oh no, who done that? Whoa. Oh, that's a bit scary. Right, by the powers of modern YouTube, let's see if this works then. Ja. Oh, yeah, sure. Oh, okay, Julia. Oh my lord! Look, we're all live on the live on screen as it happens. Yeah. What's happened to that then? What did you touch? Yeah, sure. Okay. Bom bom. Bom bom. Okay, Julia. Oh my lord, look. So I've got this coming back through the HDMI. Boom, boom. Oh my lord, look. That's you clapping. Boom, boom. Oh my lord, look. Boom, boom. So who's up first? Who's the first group? Oh my lord, look. Boom, boom. Oh my lord, look. So we're going to test live streaming. Huh? So, you're right. Do you want power? This is our power supply. Okay.
Never know. It doesn't last long.
That's the HDMI lead there from your side.
Okay.
Yeah.
Okay. Thank you.
Alrighty.
Cool.
Have you got audio?
No.
Who else is presenting? Is that group? Anyone else from any of the other groups? You love this one.
Yeah, because I reordered it so many times. It was re.
These, I need to look at it for tomorrow morning. But that should be okay. It should be okay. If you run around. I would love to skip it because they're not in the show. All right. I'm following the around the camera. Oh, so mainly just this skill. I'm going to have a coffee. Jakob, are you okay for a second? This is our one. Okay. That's ours.
can unplug it.
Let's plug in. It's all there.
Yeah, but I wanna go through it on here. Synthesis of kinetics, inflection, inversion, involution, kinetic interpenetration.
How long are we gonna speak for this?
Not long. A couple sentences.
Okay.
A constellation of ideas. We began with a cell, a dramatic cell. Highway shin. I think it might be too wet.
Yeah.
Hi, Vicky. Thank you. You clean up. Okay, then we talk about how we also have an interest in the elastic membrane, so we begin to work with that as the flow. Okay. I just want to make sure there are no like major mistakes. Well, library, pillow, hydromatic pillow.
Just ensure the position that will change and the other guys comes. Okay.
Yeah. Okay. So
you know that. Then you go here, and then here.
I'm still going.
Yes, you go and
Until
here
not here.
and until here, and then you until the other one. Right. So
This is
ensure
my
that.
last one.
Yes. After you're gonna speak for the ceiling, then I go to the stool. Okay. Then continue. I speak for the stool. This one. I finish with the stool, and then you
I go back to
come
soft
again to
office.
soft office. Continue. Yes.
And then we get to the crowd simulation.
Exactly.
And you start
Here.
here.
We continue with the stair. We continue to the staircase, the video,
Here.
and after the video, I start with
Make
that.
sure to talk about this. Like emphasize.
Here was an initial investigation of the building cycle and the building's day routine when programmatic activities are organized around the void. Okay. What else do you want to say?
With emphasize that within the void,
Yes.
mezzanine meeting spaces are placed.
Okay.
Then we go here, and he talks about all of this and this, and then you start on slide 47. And you go, and this is your last slide. Meeting spaces.
Can I say something also?
Slider.
Mm-hmm.
196.
Facade.
Wait, go back a little bit just so we can show something. Do you want to speak also? Okay.
You speak about that.
Yes.
Yeah.
Go back. Here. Okay. Then no, to the previous one. Okay, I'm gonna speak for this, for the light
Oh,
bulb.
this does this.
Okay. This is to investigate the during the prototype phase, creates a floor plan comprises of necessary spaces that serve to facilitate the levels of interaction presented by the social continuum with the course of the chance encounter existing throughout the space. Okay. Yes. And then I got here and I say soft surfaces create this scale of autonomy to interaction through the implementation surfaces become both occupied and wayfinding. The chance encounter is linked directly to surface reconfiguration. Can I say something for the color so that the color represent
Different levels of social engagement. I mean, we already talk about the social continuum.
different levels of social engagement.
Yeah.
And then record when you fade the audio in. Is no one else presenting the Okay, and then I'm going to the two slides.
Just a top tip, if you tell anyone who's got audio,
Yes, we create these different interactions of social conditions across the same
so
layer.
you have to go into your preps and make sure it's not coming out of your headphone jack, it's coming out of the HDMI.
We introduce edges that because of the differentiation,
yeah,
we're able to remove the situation in the case that correspond to social situation. Okay, that's all. And then I go here and say, here we see across the stage of the scene in the varying degree of sectional conditions
It can create.
it is able to create.
Yeah.
Then, because of the variation of sectional conditions, we deliver a variety of furniture, social and program arrangement across the same floor. These arrangements are able to accommodate changes in occupancy and program distribution.
everything already for that.
Okay, that's good.
Where did this start?
Huh? Oh, does this start on? Oh, the computer did not have memory, so we gave up on that one.
Yeah. So, did you check all the videos? Because last time I found videos that start with a click
Which one?
at the beginning, probably.
They should all be good.
Something like that. This one. Can you check all of them? No, this start. You see? This one. It's okay. This one. It's okay. All of these.
They should be
Okay.
fine.
Okay, okay.
I checked them all.
Go down to version now.
Seems like I have 8 pages, right?
Yeah.
But I have 7 chapters to write.
Wait.
Oh, I think the extra one is
Wait.
this one.
Okay.
I don't think I wrote anything for. Oh, okay, no, because we have pneumatic,
Yeah.
and then we have the hydromatic.
Okay, this is new.
This is new. Yes, I'm
Okay.
sorry.
Okay. I'll
But you
speak
know
about.
what to say about
Yeah,
that.
You can say that. Here we can see the formation.
Based on the hydromatic
Hydromatic
grid that
mechanical.
we researched,
Yeah,
we applied
The
on
hydromatic
the
pillow.
0 to 1 floor
yeah.
to provide.
Shelter from the
Shelter.
element, passive shelter for the from the elements for
Yeah.
those who are occupying the ground, or those who are passing by the ground.
Okay, thanks everybody. We're gonna try to kick off what should be hopefully a good 2 days worth of conversation. Thanks everybody for joining us. My name is Theos Paropoulos, for those who don't know. Get the chance to introduce the course and the research that we're doing here, which will be part of the 2 days event. So just to give a window into what's going to be in conversation, and also to give a bit of a window of some of the critics that have joined us for these 2 days. I'll just give a very brief introduction to give a bit of an overview of the place, the research, and the kind of things that we're trying to explore. So we've been working within the DRL on a subject that we've titled behavioral complexity, and it's been a research agenda that we work on for 3 or 4 years as a kind of umbrella, overarching kind of question, which is really about sort of exploring kind of new approaches towards architecture, implicating ideas of robotic production, implicating ideas of scenario-based design, exploring computation that is trying to negotiate forms of production, ideas of generation, in a more generative approach, and also exploring kind of a certain attitude towards sensing, machine learning, different kinds of aspects that we feel are kind of opening up new territories for us to consider as we're sort of exploring architecture in a more expanded field. Within that, this is the second year's worth of research under this agenda, and it's been building up on things that we have been exploring, sometimes at the scale of urbanism, as 2 research agendas ago that we had titled parametric urbanism, moving towards prototyping in our proto-design agendas, and that aspect of making, thinking, and exploring a digital analog kind of exchange is very much a part of our working methods within the studio. Within that, we have 4 respective briefs that you're going to see, and the way that the day is organized, you'll see 3 projects in our morning session. We'll take a break for lunch, and we'll continue with another 3 projects and a keynote lecture, which Adam will be giving to us this evening. With that, the 4 studios, just to give you an overview of this, we have Patrick and Pierre working on a studio that's exploring aspects of kinetic architecture, really looking at a certain kind of approach that Patrick has called parametricism, and seeing how that can be an expanded conversation within primarily an interior fit-out, a redesign of the Design Museum as a workspace for Zaha Hadid's headquarters. We have Rob Stewart-Smith working with Tyson, looking at the subject of swarm printing, looking at how we could use deployable drone technology as a strategy for basically deposition-based systems of production for generating architectural space. We have Sajay Bhushan, who's been exploring ideas of robotic fabrication, rethinking the concept of housing with a certain consideration of basically how we could reconsider robotic arms, and developing concepts of end effectors, challenging certain notions of plastics within architecture. And lastly, the studio that I run with Mustafa El-Sayed, which is exploring ideas of high-resolution, high-population systems of self-assembly, mobility, and self-structuring. Throughout the day, you're going to see each of the different briefs. The students will situate their thesis relative to these different kinds of overarching thematic topics. Each of them has basically been working on this for about a year, to give you a bit of a window into that. This work is, I don't want to call it the greatest hits, but it's basically where we've achieved within the time frame that we've had. And the conversation here sort of forms continued sort of development as they continue to write up their thesis and submit that in the next 2.5 weeks. With that, I'm very pleased to say that we have a very distinguished group of critics that are joining us over the 2 days. We can start with Yele Faringa, who is a CTO of Audico, a PhD student at Hyperbody Research Group in Delft, and obviously a friend also of the course. We have Elena Manfredini, who's joining us from Los Angeles, head of Atelier Manfredini, and also distinguished educator from SCIARC. We have Neil Thomas, who's joining us from Atelier 1, also an external examiner at the AA. We have Adam Davis, who's joining us from the States. Trying to remember exactly, Chief Creative Officer of Tate Towers, who's been giving us our keynote speech tonight and has been working with people like Mark Fisher and others, developing a very interesting take on deployable architecture, entertainment, really developing a lot of the very amazing kind of stage designs, performance designs for a lot of musical, theatrical kind of performance. We're joined by Carol Scott and also Tyler Casera, who are also from Tate Towers, and Elias Nubin, who's coming from Festo. His flight's a little bit delayed, he's on his way at the moment, who's head of Bionics there, and he's going to be giving our second keynote lecture on Friday. We have other critics that are coming along during the day. We have Helen Castle, who's joining us from AD, Mario Carpo, distinguished theory professor from the Bartlett, Stephen Gage, professor of innovative technologies at UCL at the Bartlett, and others like Mark Cousins and Brett Steele from the school. So with that, I think we're going to start with the first group and ask the groups to introduce themselves in the studio brief. The students are going to be presenting basically for 20 minutes, and the schedule is then we'll have about 20 to 25 minutes discussion about the project, and then a 10 minutes to 15-minute changeover. And that's basically the schedule. We've tried to put together a document that was on your seat, which basically gives you a more detailed brief of basically how we've organized the 2 days. Each of the student projects is represented in a way, and we'll give you the schedule of basically what's happening. So with that, thank you for your attention, and I look forward to the 2 days of conversation.
Good morning. Can you, oh, okay, perfect. Good morning. So we are titling our project Soft Spaces. My name is Andrew Potter. This is my teammate Andreas and my other teammate Wei Shin, and we will be discussing our prototypical research into kinetic mechanisms and how these may be applied to the case study of the redesign of the London Design Museum for a new office headquarters for ZHA architects. So we are titling our thesis Soft Kinetics. Framing kinetics as a heightened level of phenomenal articulation serves to elevate the importance of this dynamic architecture beyond the pure physicality of its movements. Proposing a strategy of architectural softness, this investigation aims to align kinetic architecture with new developments in the phenomenological field. Infiltrating the design museum with what is termed as softness, a three-dimensional intervention is made. An architecture of soft kinetics aims to inhabit the space between input and output, the space between information and expression. So the first key component of our thesis is inflection. Free to detach from its previous responsibilities of facadism, the building's exterior is able to inflect in opposition to previous notions of its role as a surface of representation. The membrane is now able to manipulate, migrate, and modulate and assumes an ever-shifting character. Temporal modulation is the new source of this movement. Next, we are introducing introversion and softness. Forces that are ambiguously presented by the facade become kinetically alive, moving throughout the building. Through an injection of softness, distinctions between spaces dissolve, and they enter one another, invade, and subsume each other. Involution. Involution is introduced as a turn to the interior, and elements from the interior are now wrapped up, are present inside the building, and they become linked to circulation and the pathways through the building and become a wandering itinerant route. So lastly, we have softness and kinetic interpenetration, where kinetic movements allow spaces to enter and leave one another, and via transparency and other treatments of surface, spaces may be closed, but still visually connected. So we have kind of revolving around this constellation of topics: softness, fabric actuation, and the idea of inflation. So we began with the cell and the idea of an inflating cell. This is a very initial simulation. And we first investigated this hydromatic cell. And what happens, it's filled with hydrogel. And what happens when we attach this hydromatic cell to different types of surface? What type of bending motion may we achieve? And what type of sectional profile and contour of surface are we able to create? And we're also interested in the elastic membrane and its relation to different types of folding. So, so we investigate this fold and what happens when you press a surface. And the creation of our fold libraries was a research into what types of sections we can create and also what types of spaces we can form beneath and on top of these folded surfaces. Continuing with the idea of inflation, we move beyond the cell and begin to investigate the hydromatic pillow. And what happens when this pillow is now applied to our folded surfaces? What type of articulation are we able to create over a pre-folded geometry through this hydromatic inflation? Beyond hydromatics, we also investigate pneumatic inflation and how through constraining a tube attachment, we can achieve a surface articulation. So here we can see, based on what side of the surface and how these things are curved, we can fold the surface and we can create planes. And looking to precedent, these are two key precedents for our ideas of curved network and soft fabric. So either a kinetic body that, in the example of the GINA concept car, a kinetic body that's able to articulate a lycra surface, or with the Philharmonic stage, a curved network that is able to rotate and give form to a soft surface. And this is an initial trial of our lycra and curve investigation and what type of spaces these begin to project onto the ground and how we begin to mark space through the simple act of depressing a curve. So the ceiling curve, this test presents an initial with this prototype, the idea of spaces formed extends to cover the entire ceiling, and by this method, to kind of create ways that surface becomes occupiable. It becomes more than two-dimensional. It extends into the space. And two specific examples of how the ceiling is maybe able to depress partially in the idea of a gallery, or in an office space, it can fully enclose or become free depending on work needs that are required. And here we can see next, this is looking more towards our future architectural intervention, but how across this surface we begin to introduce different types of fabric with different levels of transparency or elasticity that begin to add an additional level of information to this soft surface. So here, this is a prototype of breaking a surface with another surface, where one surface may pull back and then push through to create a double layer idea of this ceiling articulation.
So continuing, within our variety of soft environment, we are also looking to introduce an elastic behavior. This present as a furniture element. We call it the jumping stool. So the inspiration of the motion comes from the elastic behavior of the horse-tail spore. The stool's flexible wire frame, in combination with the lock and release mechanisms, enable the recreation of the spore's passive movement. So the stool jumps and is able to secure to the ceiling. Because of this, it can create a free space on demand or a seating arrangement on demand. This feature combination with its flexible, lightweight character allow it to relocate throughout the space.
So combining these investigations in prototype and modes of actuation, we've come to term our office the soft office, and elements of flexibility begin to emerge and suggest a new typology. So in contrast to historical architectural examples from Tati to Frank Lloyd Wright to our current the current trend in office design, which is the den-in club, the soft office aims to provide like a gradient degree, a rearrangeable, reconfigurable degree of autonomy and interaction. So the social needs can be controlled by the soft system. And working along the idea of a social continuum, previously chance encounters were limited to programmatic adjacencies, but now with the soft office, the chance encounter is able to proliferate throughout the space. And the chance encounter is something that has been key to developments in biomedical and healthcare fields, and something that is essential to the exchange of information. So working from the inside out of the Design Museum, we aim to first propose our interior strategy of softness, and then a flexible membrane that is able to accommodate these interior reconfigurations. So the Design Museum, for those of you who don't know, it's located on the south bank of the River Thames in Southwark Borough. And the key feature of this site is its bridging of riverfront and neighborhood. So we aim to connect these two components through our three-dimensional intervention and create a dynamic interior passageway for public users and the office users. So to do so, we have utilized the human cone of vision from different key points of visibility, up to down, bottom to up, and from different statuses of standing versus seated. So we use these cones of visions to intersect our slabs, and this is how we generate a dynamic void space up through the center of our building, something that we imagine where the itinerant circulation to take place. So this void cut begins to define two key building segments, a publicly visible front and a more internal, or a more turned in office back. And so this is where we place our vertical, oh no, sorry. Where we begin to place our vertical circulation element. So it's this spiral stair and mezzanine combination that connects levels 0 to 6, but also we introduce mezzanine interstitial floors that become our meeting spaces. So we bridge the full building, and then we create these platforms upon which activities may take place inside of this void. And it's something that people will move throughout and experience different changing points of focus and vision across the path of this stair. And so moving through, we begin to experience the platform, and then we can arrive at a gallery space where then our soft ceiling becomes actuated and begins to form a space on this level.
So, here we see an initial investigation of the building cycle and the building's day routine when programmatic activities are organized around the void. Within the void, mezzanine meeting spaces are placed. The ceiling network investigated during the prototyping phase creates a floor plan comprised of nested spaces that serve to facilitate the levels of interaction presented by the social continuum, with the goal of the chance encounter existing throughout the space. Soft surfaces create this scale of autonomy to interaction. Through the anti-formation, surfaces become both occupiable and wayfinding. The chance encounter is linked directly to the surface reconfiguration. The colors represent different levels of social engagement. So we create these different iterations of social conditions across the same level. We introduce agents, and because of the differentiation, we are able to recognize change in behavior that corresponds to social situation. And here we see a frozen state of the ceiling and the varying degree of sectional condition it is able to create. Because of the variation of the sectional condition, we deliver a variety of furniture, social, and program arrangements across the same floor. These arrangements are able to accommodate changes in occupancy and program distribution. The soft reconfiguration of the interior becomes translated by the facade. Shifting social scenarios indirectly play out upon the facade, as we can see here to the floor plan.
The facade is composed of two major systems, structurally contoured and perforations. The structure contour consists of a primary and secondary network, while perforations respond to either the surrounding or internal conditions. Corresponding with the building's division into 3 primary zones, the facade is divided into regions that are controlled either by pneumatic or hydromatic expansions. Perforations are most dense along the primary contour lines, serving to open views for the river and riverfront or increase the building's volume. Specifically, perforations are concentrated to allow visibility to gallery and public areas from the riverfront and are less dense at the rear where they relate to the work environment. Secondary contour lines are linked to the previous described shifting social scenarios. Our investigation into the ceiling mechanism attempts to create a movement that joins facade expansion and the contract with ceiling behavior. A facade that, by a rigid architecture, would be a solid line is now able to breathe and expand. In this way, we create a surface that has a habitable dimension. Surface now becomes occupable, and the facade assumes a new responsibility. Pneumatic actuation, stemming from our interest in inflated folds, is applied to primary facade contours, while the surface between primary lines is deformed mechanically and related to interior movements. Hydrometric actuation exists at level 0 to 1 and is implemented in order to shelter occupants and passerby from the elements, locally tailoring the facade's behavior to environmental conditions. Ultimately, when seen in it entirely, the difference in surface created by primary and secondary contour becomes clear. The difference is clarified by the degrees of perforations opened and the visibilities created, as well as the degree to which new volumes are expanded. These changes take place above 0, 1, clarifying the difference between pneumatic mechanism and hydromatic regions.
So, in conclusion, we aim to integrate these 4 interests of the soft surface and its the way it can be manipulated to create this office type that is free to create varying degrees of autonomy, and to link this office type and its social relationships to both the interior soft surface and how the motions of this interior soft surface are then radiated outward through our mechanical and inflatable facade. So thank you for listening. Okay, so you can explain.
So here we see our initial studies to the pneumatic system, hydromatic mechanisms that are attached to the surface. So we see the surface without the deformation. The second prototype, we see the activated one. Here we see our interest in the surfaces and the deformation we could achieve. So continuing, we see one chunk of the building in a scale 1 to 20, a frozen state, that we can see the primary facade, the secondary facade, the perforation system, and also the soft ceiling into the interior with the diffuse light and some arrangement of the furniture. And this is the whole model of the building. So here we see the facade, a frozen state again of the facade. And if we this building of this model is 1-to-1. And we see the again a frozen state of the soft ceiling. We can see also the void, the staircase.
It's an element of our circulation and our cut.
Yeah.
I'm sorry. But anyway, so yeah, and one frozen status of our soft ceiling and the furniture arrangements that may begin to be defined by this ceiling deformation.
So here we see a segment of the previous iteration of our facade with a perforation system again. And this is the two prototypes, the first prototype of the jumping stool and the second prototype of the stool. And sorry, yeah. And here again in scale 1 to 50, yeah, we see the soft ceiling with the the curve network, yeah, and the curve network, yeah, for the whole.
And then some study models of our mechanism and how we're going to begin to deform the ceiling surface. So
Thank you. Can you go back a little in your presentation? I just wanted to understand the way this thing was generated. Your idea that you take a building.
yeah, so it's like a parametric cone of vision, so we can draw a line between if we have an office program at the upper level, like the plan is to connect the two levels, right? So based on the length of this line drawn between spaces, we can determine the shape of the cone of vision. And
specifically for this particular void you created, you've chosen some
yeah.
cones of vision and cut holes through the floor, right?
Yes, correct.
Okay, I understand that. And then the next thing is your idea of using flexible surface in the ceilings to kind of change the way the spaces you relate within those spaces.
Yes.
You chose a series of social uses. You described different uses around the building. How those diagrams there? You've just chosen arbitrary ones for now, and they can evolve and change all the time.
Exactly.
I'm really interested in the idea of what the kind of speed at which this thing happens.
Mm-hmm.
Because it seems to me, is it something that you can change the spaces throughout the day?
Yes.
So, and I guess the thing is, assuming floor plate is whatever size it is, and there are however many people in that space, who decides how that happens and why it happens and when it happens?
I mean,
that has a huge impact on what you're talking about.
So I mean, it can be varying degrees of temporality. Like one floor could be long-term. Like if a floor needs to be high occupancy, if there is a lot of work occurring on this one floor plate for like a high activity work, this floor could become a hive office, right? And then on a lower floor, if people need to have a discussion, then alcoves can form. So maybe this is probably not answering your question, I don't know. But it is on-demand space, or as on-demand as possible, given whatever furniture needs to be reconfigured. Does that answer?
So I really, the idea that actually you can change the nature of the space during this day's use, I'm really interested in. I mean, it's something we've been kind of talking about through other projects we've been doing too. Then going on to the facade, but I didn't quite get that.
Okay.
You suggested that it kind of could change through pneumatic. I mean, here you're inflating it there.
Yeah.
Right, and you were suggesting you could expand the building, but you can't actually expand the building with the floor plate of the building, can you?
No.
You can change the shape of the facade or internally the facade. So effectively taking your ceiling idea and wrapping it around. So it changes, you push into the volume.
It can expand in the sense that it creates a higher surface area on the facade to open more perforation or to create more view, or to create a smaller occupiable space at the perimeter of the facade for like a discussion or a smaller group interaction. So it's not creating per se floor plate area, but it's creating an opportunity for more like spatial typologies to emerge, I guess.
No, I have one other comment to make in a moment. Maybe somebody else can speak. But I love your, what do you call it, a jumping chair?
Yeah, jumping
I
stick.
love it. I love it. But I mean, clearly you understand the nature of scale of that. Can you imagine trying to get stick to the chair to that ceiling?
Well, luckily
Honestly,
we don't have that high of a
build a
ceiling.
full-size one. I'll come and see it. I'd love to see
Okay.
it. Honestly. No, good job, guys. It was seriously. The idea of these kinetic space, changing space, for me is a really fascinating world to look into. So I would be interested to see how far you can go with it.
Thank you.
I think the project is quite ambitious in the amount of program that we are taking on, and ambition, also technological ambition. I think one thing that is interesting to me that still architecture tries to make animated buildings. So things that are not animated, they need to find life. There is this idea of the author making something that has life on its own, which I find quite present as a no matter what architecture does, there is this idea that your own creatures have their own life, which I think has nothing to do with contemporary architecture. It's something that goes through every centuries of architecture, and this project really tries to do it at every possible scale. Probably the one question I have is how you turn the corner. It seems like the project is has an approach in terms of ceiling, an approach in terms of floors and facade. When it kind of needs a second round to me, where you can put them all together. It seems like you're still based on quite traditional way of understanding slabs and attaching your system to the slab. And I think when you turn the corners where the two things come together and not yet in the fluidity that maybe people will find accessible. But I think it's just an issue of the length of the program, how long you've been working on pieces, and the pieces came together at the end. I think you would need another round to really understand how this and this, and if they do, they come together. This is the first model where this happens, and I think it's the most successful one in many ways. But there are moments where you actually start seeing this, and you understand how they're detached, how the skin is detached from the interiors, and how they don't work together in many ways. And I think here we start to see it better, and probably just an issue of fluidity of design. Maybe you can talk, because I think the crowd and the program are always our excuses. Even the corner vision, at the end of the day, you always go to traditional ways of design and say corner vision is the way in which I'm cutting the floors. And I was hoping actually for something else, not because that's not correct, that's the correct answer, but somehow it's the traditional answer, or a flexible office space seems to be the excuse for mobility. I'm wondering if there's another narrative that is less pragmatic and more true, I think, to the nature of the project. Somehow I think there is always this traditional way of explaining the project, which probably is not needed in here. I find it traditional, weirdly traditional, I don't know.
We're still looking for rationality. I mean, although within this overall rationality, there could be zones of ambiguity and mutation and chance, like you mentioned also in terms of the chance encounters, but we should also mention that they're meant to be an ordering where the encounters are less than pure chance, but more kind of relevancy oriented, because we're also having the crowds differentiated in different categories, and we have zones of designated zones with degrees of anticipation of who to expect and what to expect. That's also important. So it's not about a big mixer of randomness, but we're aiming for, that's the difference maybe between SciAc and here, for what you call traditional. The traditional label I don't accept so much, but the pragmatic label I accept, and that means there are purposes which have to do with the contemporary, and I think that there is a specificity with respect to contemporary desire for adaptation and transformation and interpenetration. A lot of the themes here, contemporary offices very different from the office of 50. But I want to pick up from one thing what you said in terms of the time scheduling of this, and I think you haven't thought enough about this. Just to say this is on demand, I think is not convincing. So I think that we could have and should have perhaps in this kind of project, if you haven't, but make that a topic and theme at what various timescales and nesting timescales something like this could be seen to be operating. And you know, there's these layers of transience one could think of with respect to structural transformations on one scale, and then the most ephemeral maybe just the mood of light or just what the occupation through the human bodies is shifting in terms of the configurational diagram. I think this is one topic which is very important. The other one is, as you said, the question, how is that activated? The difference between something which is bottom-up emergent and then amplified, or a pre-scheduled scenario, and on-demand is also kind of a rather vague phrase. Whose demand and how is that processed? So I think, so at the moment we have just that vague hint of a machine which can do lots of things, and the scenarios are not explained enough or not thought through enough, so because we're lacking categories and terminology to do that, so that just to as a critique. Yeah.
I think if I were you, what you might do is consider the use of the spaces through a particular day. And it's a kind of interesting thing, the cause and effect. Do the spaces drive the occupancy, the way you change the roof, or is it the other way around? That the occupancy drives the spaces? I mean, that's a really interesting thing to consider then, because then the way your surface changes, you know, you can begin to manipulate the way people are working. I know that's slightly perhaps Machiavellian, but it doesn't matter. The point is, that's what I'm interested in this idea, because once you've got that, what these spaces, how you can change the way people move into these spaces, begins to suggest what these volumes are. And that's fascinating.
Again, you haven't taken that obvious question on enough, and of course it should be, in my view, both. There's an element of an active element of the reconfiguration, which then channels the bodies, and that could be driven by management, or it could also be, in my view, partly spontaneous offerings, and there could be a feedback, of course, where of training these machines, as it were, and machine learning. But of course, it also would be the action comes from the bodies, and then there is just responsiveness. This is making space for bodies which fill a space, following a trajectory of somebody, a little group gathering, and then an enclosure detecting that and amplifying that. So there is responsiveness, responsive environments in that traditional sense of an interaction where the action comes from the users. But I think there's a dialectic here, obviously. And we should think of positive feedback loops and negative feedback. The whole cybernetic conceptual universe would come into play. Yeah.
Can I ask something though? I understand the ceiling collapses. It doesn't ever close the space, am I correct?
Yeah,
it never. And how then, and that's my major question, and that's why I asked how relevant really is the pragmatic of that motion, because it seems like it would influence the way in which you move, but for instance, not visibility or not acoustics. And so maybe in an office, it's just simply a way of embracing visually, but not necessarily answering to a real pragmatic differentiation of needs. And that's why I said what I said, that somehow there is a more experiential quality rather than real pragmatic response to a programmatic need. And that's the reason I find that the need for a pragmatic explanation sometimes it's less supported by actually what happens as of now in your schema. That's my question.
I mean, to shoehorn it into a pragmatic project is maybe
Isn't it?
So
I
it
agree with you.
is an experiential, like you move along this curve and it is an experience. You move along
Yes,
this depressing
I
surface, it's an
completely
experience. You're folded into this membrane, you're immersed, embraced by it. So, yes.
But I think we're making a false distinction. I'm embracing experience and spatial character, the phenomenology of how something appears. But this is to be thought through as instrumental, because this influences behavior, and that should influence behavior and can influence behavior in ways which are intended and become pragmatic. So it's the pragmatic through representation, through atmosphere, through experience. I mean, this is not a ride, but it's an experience where people are they're intuitively brought together, put into a certain mood which signals the character and quality of the social situation. And then the situation has a better chance to unfold in ways which are relevant, and people are brought onto the same page, as it were, experientially, to have these situations evolve. So that dichotomy has to be overcome. In my discourse, everything is in the final analysis pragmatic and instrumental, but we're not doing it as a kind of engineering agenda where it is all about there's enough space and the door is big enough for people moving through in a certain time schedule, but it is about the space is legible, is suggestive of an occupation. It signals, the event signals its presence, and then we come together and we, in the semiology, we can grasp the informal character of this gathering versus the formal gathering of that space, and these become the instruments and leading to a criteria of success, which in a final analysis about the productivity of these exchanges taking place. So it's a more soft pragmatics, if you like, in terms of soft science, but still something where we have to employ these rational strategies. And even in those can be, in a final analysis, mathematized and get operationalized when we model some of these things with the crowds. We've started to do, but not haven't. It's just a hint.
I like Neil's comment on the question of scale. If I can briefly expand on that. So maybe it would be interesting for you to know a little bit more of the science of allometry, which relates, let's say, the body size to its anatomy. So for instance, if you look at the section of a bone, if you compare a grasshopper to a mouse, to a dove, to an elephant, if you see the section of a bone, it scales logarithmic, exponential to its bodily mass, right? And the thing is that some of the most lucid work of your project, this chair, it's such a lucid idea, but as an architect, it's problematic if you're a bit naive to the question of scale and mass, right? And also because you're dealing with the topic of a flexible architecture and why it's difficult to make these shapes move in an elegant way, because it's difficult to shape a lot of mass in an elegant way, right? It takes a lot of engineering, it takes a lot of heavy machinery, and some of your parts of your proposal that I think are elegant achieve this, but so some of the work does this very well. Some of the other elements are, undercutting this effort in a sense. And finally, what I think is admirable in your project is that, a traditional point of view of design is determinacy, right? There's kind of an ultimate outcome of a design brief. The way Theo van Doesburg formulated, right? There's a mere consequence of a simple idea. So if you introduce this idea of flexibility in a project, right, you introduce indeterminacy, right? So arguably a project can also become programmatically more bland. So you've dealt with that in an admirable way, I think. But if you look at one of your earlier simulations, we see the building working at one moment in time. right? And I think you need to think of scenarios of how the studio would unfold in different moments in time, right? How would it work on an early morning in March? How would it work in an afternoon in December, right? Could be very different scenarios. So I think, let's say, this concept of time could have been more fully determined. Yeah.
Can we pass the microphone down this way as well?
Can you explain a little bit more about the differentiation between using air to actuate and using fluid to actuate? You guys mentioned hydro, and I wasn't quite clear why you were choosing one over the other.
Okay, yeah, so from this portion we're using, like from 0 to 1 slab, I'm going to use the water actuation as a passive response to the environment to shelter people who are moving along the building or entering into the building, but as to create our vestibule or transition space in inclement weather. But then because there's releasing programs for so we're particularly using the air-based ventilation to into a certain or required movements. So this is like a passive, more passive level that I can respond to.
Is the idea there that you're using the fluid because it's more solid and it's not moving as quickly?
Oh, no, just because it's something that can respond to the rain and create a covering for people who are in transition into the building. Yeah, also, or, you know, it's not because of stuff, but yeah.
The other thought I have is the stool, as fascinating as it is and interesting as it is, I do think is slightly detached and doesn't necessarily belong amongst the rest of these studies, meaning you've got this really incredible thought process of how to make a truly kinetic building, and there's obviously lots of ways to have transformable furniture within it, and I don't know that that piece of furniture is necessarily right, and it almost distracts from the work and the quality of work. But it's very well done, guys. I'm impressed.
Can I say one interesting, talking about the chair, what it did for me, scratch the surface, something that I think is more interesting is what furniture is, what furniture we're now using, because we've been sitting in the same chairs and desks for hundreds of years. You're describing a space which is much more fluid, much more changeable, and therefore you've got to rethink the way people work, actually, which is what you're beginning to talk about with your chair. You know, you have a chair that disappears. That's what you're saying. That's a really interesting thing to think about. Is if you're changing these spaces and you're moving people around, as is suggested in some of the things. I mean, look at those drawings there. It's almost like you've avoided drawing any furniture because actually it's a big question. What is it? I'll pick your table up and move around with you. It doesn't work. So I thought that was what came out of me from the chair.
Can I just ask what you've done about considering the acoustics as the people are moving around the building? Because it would seem to me that if you have a cluster of 100 people working in one area and then you have a cluster of 20 people or 10 people working adjacent to them, their environment is going to be completely swamped by the noise from the first area, and it's not going to be conducive to being open plan. How would you deal with that?
I won't disagree. I guess with that, I would say that's probably an underdeveloped portion of the system, but
Can I say, I think you could probably be very clever and you could probably take the movement of the ceiling and make it into mushrooms and acoustics at the same time, so that you could actually build that into the whole management of the building. So if, for example, you knew how many people were going to be in an area at a particular time, you could actuate the ceiling so that it could deal with the acoustics.
I think those comments are quite important because they start to drive at some of the questions that Neil opened up, which was actually like, what's driving this? And I think it's more than on-demand acoustics and other atmospheric aspects that it could make this actually something that enriches the daily environment, or if you don't deal with it, actually becomes just a noise and just a mess of actually just movement and chaos. So that sensitivity, I think, is something that you can still sort of develop a little bit, and I think you're in a good position to actually explore that. But I think to do that, you have to actually also make, I think, important distinctions that change is not necessarily for the sake of change. It becomes an instrument. The control systems that are going to drive this are not linear and they're not singular in a kind of reactive way. And I think that's where this kinetic discourse has evolved quite a lot, from particularly also some of the early responsive environments. It's not just about on demand. That stuff, to be honest with you, from a management perspective of how an office runs, is quite clearly somehow addressed. But from all of the other aspects, from how office environments are changing, the consultants, the different characters that are really going to be operating here, I think you have the opportunity to really explore that, I think, much more explicitly.
I mean, I want to come back and talk a bit about phenomenology, because that's some of the slogans you've put up front. And you've just left it as a phrase, and you haven't come in, for instance, and analyzed a field like this, how it is decomposed in a series of spaces you recognize, how the color coding here is actually delivered with the ceiling configuration. When is the ceiling coming down? When does it start to create a space? And what is the expanse of the space? Where is the center of the space? What is the orientation? This would be a gestalt, a figure recognition out of an amorphous field when these figures crystallize. And I think how that could be supported by light, the ambient parameters, so these are observer parameters, ambient parameters, and then at that point, the acoustic become interesting potentially. So there is an engineering aspect of lighting and acoustic in terms of just pure and disturbance levels or sufficient light levels. But for us as architects, we go on top of that, we take that for granted as a minimum, and look at them as organizational substances, phenologically, in terms of perceptual papillity, conspicuity, and then the semiological signaling. And we can now, with the medium of light simulation, bring that home. But we also know, we've done it before at DRL, that we have now acoustic simulation engines where you can actually have the same event or noise source, which might be the people talking themselves or moving around, sounding very, very different in different acoustic conditions through particular reverberation atmospheres, and also what is coming in from the outside. So for us, I think we have to recognize that the acoustic orientation in a space and also the signaling of events through acoustic transmission is an element we could start to work with, and we can, as we now have potential to have that as a simulation running in the background or exploring the design. That would be, and not that we have done this here, but just throw this in, that we would do it, and it would be part of a phenomenological investigation of an orienting medium, a structuring medium, what is, and if that bleeds through the whole building, then there is a unified event, and how much you can kind of segment this out and switch the acoustic atmosphere. It's also an atmospheric thing. You come into a room which suddenly is very quiet and dry and swallowing up all the sound and makes everybody quiet perhaps, and then you know it's individual, not like a library atmosphere, or one where the sound is amplified in the social space and kind of announces its kind of echoing vibrancy. So that would be the architectural take on the acoustic conditions. Yeah. Okay, thanks everybody.
Or keynote, sorry. Yeah.
Can you convert it into a PowerPoint?
Yeah, it will take like 15 minutes probably. It's quite large. Okay.
bum, bum, bum. This is super.
How do we connect? Thanks. How do we connect? HDMI, right?
Just grab these. Take it to the studio. Stick the blue tack underneath this. Try to help her fast.
Can I check with you? Can I check with you? One. Is everything on? Can I check this with you? I don't know. Maybe need to. I don't know. Just let it be. Don't do stuff. Push it. I just want to close. It's not being safe in the flash drive. I'm not talking to this, right? Isa. Where is Isa? Shit. There are lots of panic, right? Which one? Never ever white furniture. Never ever. We'll see. Do you know which one?
You're not showing up now. You're not showing up in the projector now.
discipline is one of our major requirements. Can you say something? Why? Just we have done simulations. Don't say anything. We have also simulated. In this simulation, we can show how this procedure. Okay. Thanks. Autonomous.
Good morning, everyone. Ritu, Isa, Asad, and I, Maria, form Project Plinthos. We are part of Robert Stuart Smith Studio Behavioral Production, which explores swarm 3D printing with an ecology of semi-autonomous aerial and ground robots. The studio aims to use this aerial system to compress design and construction into a singular real-time creative process. The brief proposes architectural speculations that rethink on-site construction as adaptive, rapid, and on-demand.
We see multicopters. We see multicopters as having great potential for design and construction, as they offer pre-3D flight mobility and range. These flying robots are already becoming important tools in numerous fields and are used in many different applications, such as surveying and mapping, transportation of cargo, and inspection. Multicopters come in a range of sizes, each capable of carrying a different payload. Our project envisages 800 mm diameter multicopters that carry payloads of 5 kilograms. Our research utilizes smaller copters suitable for indoor flight that carry a much smaller payload. Although constrained by battery life and lifting capacity, when used as distributed agents, they have the ability to build architecture cooperatively in a strategic manner.
In conventional 3D printing techniques, FDM prints its own supports while SLS uses a powder bed. In construction, this gives potential advantages such as quicker output, lower labor costs, and less waste produced. However, the method requires big infrastructures that are difficult to assemble and are not mobile, which limits its possibilities. By linking the flexibility of aerial robotic movement and conventional 3D printing techniques, we are proposing an aerial printing method for construction.
The presentation will be split into three main parts: thesis, research, and application. Our thesis investigates the use of sand dunes play a key role in our main strategy as they serve as natural scaffolding for construction. Material is deposited on top of them to form a structure. We use sand and water as locally available, locally sourced materials to build these structures. Then we go into research. process of aerial 3D printing is a result of three main factors: material properties, the behavior of the print system, and flight behavior. The research proposes using sand and water as locally sourced materials to form a semi-liquid mixture with specific elastic properties. Specifically, we researched a binder that is able to provide us high particle cohesion and is able to form a viscous sticky mixture. Working unsupervised, our UAVs would require to have printing hardware that would refill and print on demand. So we developed a hardware that uses a lightweight linear actuator and syringe that can be attached to UAVs via an onboard computer. We developed a large number of 3D print hardwares that were suitable for this for this purpose. We realized that the main problems were firstly regarding distribution of the weight itself. It had to be distributed along the center, and this was important for any form of flight behavior on a quadcopter. There are also the payload limitations of the quadcopter itself. We chose tethered flight, which allowed us a greater range of printing capability and a larger amount of payload capacity. Continuous material, sorry, just a minute. Specifically, we were looking at material flow, and we cataloged certain mixtures that were able to provide this with the regulation of the binder. Printing in the air shadow area was the main concern. This is the area in which the effect of the propellers do not affect the printed matter itself during deposition. By combining these factors, that is distributing the weight of the mechanism in the center and having a sticky mixture, we're able to produce continuous flight printing behavior.
Computer-controlled flight is essential for aerial 3D printing. IR cameras provide an off-board coordinate positioning system, and additionally, we have developed an algorithm that generates a design proposal through a simulated construction sequence. Additionally, we have developed an algorithm that generates a design proposal through a simulated construction sequence. As refilling was one of our major requirements, we created a responsive system where the aerial robot is aware of material refilling and continues to execute printing as from the last printed point upon printing the payload. We have also simulated this autonomous behavior, as this was a major requirement for our system. Using the onboard camera vision, we were able to form stigmergic rules for aerial 3D printing, which is able to form a closed loop system for construction. Taking into consideration the material behavior hardware system, which gets the criteria used in this environment, we introduce a responsive system which is able to configure flight paths that arise out of simulations of real-time flight scenarios. The cyclic behavior of the print system and flight behaviors and the material behavior, we were able to create a continuous flow of material from a flying machine.
In our simulations, we are investigating three types of relationship. Multicopter to multicopter, multicopter to material, which is the perception, the multicopter hearts of its trail, the stigmergy, as we have seen in the previous video. And multicopter to landscape, which in this case is the desert and the sand dunes. With these algorithmic procedures, we are able to generate the design as a construction sequence. In our simulations, multicopters are controlled by agent-based logic that controls its position by vector calculation. It also looks after material and battery refilling. We have developed simulation We have developed simulations that control different patterns for construction over sand dunes. And having different patterns, we were able to control which were perform the better. But a single layer of material was not enough for construction.
Application, we're going to talk about application now. In a desert, there are actually many different sand dunes geometries. They are affected mainly by the wind's direction and speed. We are proposing our scenario in a remote environment where the materials as sand and water are locally available, and we are proposing to use the dunes as natural scaffolding to structure the printing method. The world is suffering from a process of desertification. Due to climate changes, the world is being through a process of desertification. It's an issue that threatens more than 1 billion people in more than 100 countries. Desertification is occurring fast. The projection is that by 2050, arid areas will represent more than 20% of the world's land. To help reversing the situation, there is a technique called desert greening, which is the process of man-made reclamation of deserts. Oases are formed. The greening of the desert is reliable mainly on the water source. Oases are formed by subterranean rivers that go into the surface in a desert. We are proposing a system that can remotely through satellites scan the areas that are better for this application, the deserts, and find multiple different locations that could be regreened with this technique.
We were developing prototypical structures and we're running structural programs in order to see our possibilities according to different choreographies of the multicopters based on simulations. But again, our initial problem was that we couldn't achieve structural depth. So we continued with some more constructional sequence process. As in this case, we introduced the column as one of our methodologies.
As a strategy for the construction sequence of the models, we are proposing constructing multiple layers to increase the structural depth of the structure. So the construction sequence would be based in having the sand dune as a support, then printing one layer, adding more sand adding more sand to elaborate with adding more sand to create this increase of section, then printing a second layer, adding sand, printing a third layer, and so on. We tested this principle of the columns with some basic structure simulations in dome-like structures, testing different patterns and how the column alleviates the load in the structure. We also tested different deposition sequences and patterns through physical models, testing how it would behave and how the material and the section would behave structurally and architecturally. So after the column, we still had the problem that one layer of material was not enough to carry the structural load. So we developed other technique to create spatial frames, adding small columns in between each layer, connecting them, and in this way increasing the cross-section. We also tested the same principle with using the copter, printing with the copter, when we use these small parts of sand in between layers, creating the same space frame.
In all these applications so far, we were using dome-based structures, but we wanted to develop more, to get into more dunes formations and shapes. And we started thinking more about rules, keeping in mind stigmergy and alignment into the trails, as we had as we could have real-time decision-making based on camera vision. We thought about alignment and branching as two of the main rules that could potentially increase the density in each of the layers. But in reality, we are using this same alignment procedure in order to align to the next deposited layer after sand is being moved on top. In this section, we can see that for a shelter to be constructed, multiple layers have to be added on top, which keeps the cell structure rule that it has to be thicker in the bottom, thinner in the top because of the loads. In this, we have selected this dune, the S shape, taking into consideration the wind, and we have developed the simulations in order to gain the pattern that we could have in our design. As satellites could identify the potential locations of their certification and find the best place for greening, UAVs and ground rovers are airlifted while scanning process for a suitable construction site begins. In this case, an oasis had become had played a key role in our design, according to which the self-organization of the copters took place in the periphery of the dune, in this case, the one that we see. we can see the basic logic based on which the rovers and copters are collaborating in order to increase the section. And these pathways were generated with processing based on the routes that the rovers, which will bring the material from the mountains and from the lake, the water, to the basic shelter. So the proposed architectural system works on a speculative prototypical manner based on the material structural behavior and its possibilities, as well as stigmergy and real-time decision-making rules. In contrast to pre-designed traditional construction techniques, collaborative aerial robotic fabrication offers an opportunity to produce complex, dynamic, and this we can see in this page. We can see the interior of a space that how we can envision it, and we are arguing for an adaptive system that are time dependent, as our project argues for a logic where the space crafted is the result of a confrontation between climatic conditions, structural forces, and site topography. The system would then become a truly sustainable form of architecture, which uses on-site, widely available material to construct buildings that are reintroduced into the natural landscape once their lifespan has been reached. Thank you.
Here we look at some of our prototypes. I mean, the mixture that, the way we printed these models is we used the deposition system for the ones we used on the quadcopters, and we built prototypical models explaining our printing strategy. The models themselves sort of evolved over time. I mean, in a lab condition, we would be restricted to small copters. UAVs are illegal to fly in public spaces in London. Also, I won't be able to experiment so much. We use, obviously, the system we explained before. The dunes is natural scaffolding, and the logic is to create a shell-based structure completely out of simple 2D, almost 2D flight patterns that arise out of computer simulations. We tested column printing strategies. Although these are simple layering strategies, we envision that they can be possibly done by the rover.
Maybe I'll just introduce a bit the brief, seeing as it's the first team for this studio. The studio's been looking at trying to compress design and construction into a singular bottom-up creative process and fusing aerial robotics with 3D printing. And this is both a technical exploration and a speculative design one. The studio's just, because of the work on this, we've just been awarded a £3.3 million grant with the government to actually, in 4 years, deliver a functional aerial 3D printing system for construction. And that's a collaboration with a whole bunch of universities and companies in construction and engineering and 3D printing and so forth. So the technical work has been delivered to a level that it now can go to the next level. And this team's been very instrumental in delivering that. And then the design speculation work is more individual per team than the technical work, I would say. But all the work has been focused a lot on developing a capability not only to deliver that functionality, but to understand how autonomous decision-making through computer vision in real time can actually play a role in either adjusting or developing a partial or entire design through that process. So, for instance, one thing they mentioned was stigmergy, and they showed a quadcopter printing a path and then following the path. So the principle there is that
out in the desert, one doesn't have the kind of motion capture resources and everything they're using in the lab. So the point is that they use camera vision to find what they've already printed and to align to that. And so the entire design process is based on that one computer vision camera process. So the emphasis has been on the unity between these two things and developing the capabilities for that.
Are these models all made from sand and mortar? Are they all sand and mortar? With the binding agent. So
It's a metocell. It's a biodegradable ingredient that has been used in concrete for a while now.
And in a larger scale, like the thing you present there, the image, the same binding agent would give you the thing to lock the thing together so it stays stable. Okay, I have a. Is it successful architecturally in terms of the idea of creating spaces adjacent to these mirror the water? You know, I think it sounds very interesting. The idea of greening these things, that I kind of understand. As you've presented such a technical project, I feel I need to say something about the technical aspects of it, because I think some of the things you've missed opportunities. You choose to use the sand dunes as a kind of a basic scaffolding. Very interesting, clever idea. I think what you haven't done, or perhaps you have done it but haven't mentioned, is what forms that they come in and why they work. Because there will be different sand dunes that work in better ways to form three-dimensional surfaces, or the scaffolding for three-dimensional surfaces, right? And I think, so that's a piece of work if you're going to develop this thing, you really need to look seriously into, is because some three-dimensional surfaces are better than others for all sorts of reasons. Secondly, the way you apply the material to it, the layering of it. Analysis of three-dimensional surfaces is very particular. And where you need material, there ought to be a level of theoretical analysis on the surfaces which you don't appear to show. Again, you may have done it, but that will begin to tell you where you place material rather than you just, you know, maybe through tests you're doing that. But I would have thought it's worth investing on some time into finding out what where the additional layering, because your comment that it's better less on top and more at the edge is not entirely true. Okay, so be very careful about making generalized statements like that. It depends again on the overall forms of things. And again, the distribution of it, the way each of the fibers, or whatever you call them, the strands, it works. I mean, all those things will come out of a theoretical study. But as an idea, man, I love it. It's great. Seriously, if you can make buildings from sand and water, you're doing all right for yourselves.
Do you intend to bring the binding agent to the site? And is the binding agent, as a material that is scalable to take the forces of the structure? Have you guys analyzed that?
In terms of how we're proposing the structure is it forms an eggshell by continuous layering. So that way you don't rely on the strength of the material themselves as much as you rely on the shape of the structure.
And does the material, once it hardens, it will then stick to another hardened surface? And typically in a large structure like this, even if it's concrete, there's some sort of fiber or reinforcement laid within it. But you guys are fairly certain you'll be able to get the stiffness out of the sand and the binding agent without adding a fibrous component to take the tension. Sand and binding is usually really good in compression, but not necessarily in tension. It would make sense to probably do some, if you have, maybe you have done, do some material testing of that, because the entire thesis is based on the sand and the binding agent being able to take tension.
How many different materials did you look at? I mean, the agents. Did you look at a whole variety of different materials? Have you done that?
That's right. Actually, this is a binding agent is a cooking ingredient. It's used in the kitchen. So we used it in Jello and meringue and
I think the project is quite inventive, and what I like about it is the level of imprecision of a very precise system that you have to adapt to the wind, to the sand, to many of the things that actually we take for granted that don't exist inside construction somehow here completely change our way of thinking about it. You have incredibly precise machineries, and probably precise materials that have to deal with. I was looking at the deposition process, and somehow it seems completely almost random, the way in which the wind moves around your machines and how you have to find your path again. So that part, I think, completely misplaces a sense of precision that architects quite love as a way of making. The second question probably is on the line of the structural problem of not having reinforced fiber and things of that kind. I mean, there's a lot of 3D printing done with concrete, contour crafting and things of that kind. They've been doing almost for 30 years by now, and now they're becoming a reality. But also, they all face the problem of the reinforcement, and I think that's going to be part of your game. And most of all, how you then close the surfaces, because this is a non-precise system, and somehow it works as a structural system. But then, how do you, if you would want to close them, how then would you adapt to this again, to this level? Because once it's crystallized, then it has a level of precision you have to respond to. It's not anymore that adaptable, no? And how would you then create something that could be inhabited? You would need a secondary system on top. And that's maybe the other question that the project still needs to solve, like how to keep the sun out, I guess. So this yeah. If there is a question, yeah, maybe there is already an answer.
For this particular one, we were thinking of having some denser patterns in the bottom part, but to move things forward, if we keep in mind the Solar Center project that creates glass out of the sand, right? We can also...
Out of the sand.
Yeah, sorry. Then we can also argue for glass being casted, in between, which will be more...
Would the temperature work? I mean, I don't know. I am not knowledgeable on the topic, so you might guys... At MIT?
No,
okay.
at RCA. He's now at MIT.
Yeah, I know that.
And he was using magnifying glasses to basically melt the sand, and he created 3D printed bowls in glass.
And would that be scalable? I've actually seen the exhibition at MIT 2 days ago.
Is the intention to close it off? Is that they're all...
There is a possibility of closing and the possibility of leaving it open depending on the site environment or the location that this is being implemented.
Glass, of course, in tension is an incredible material. So that you put that together and you get the tension member out of the sand.
You begin to hint at sort of inserting into the unit itself. I have two things. Did you do any investigation into sort of programming on potentially the dune itself and building multiple, say, levels, circulation paths that are more than just, say, once you excavate the support material out, you're sort of left with one level. You begin to hint at it with the columns and boring sort of into potentially the dune. So did you investigate that, or were you just looking at sort of adding on top of the support? You're actually looking at adding support and on top of what you printed to then create multiple layers to this.
What we're doing is we are starting the process with different dunes, like plural dunes. So each dune becomes a space, and then as we add layers, we start varying the shape, the overall shape, combining these dunes, creating structure, and also combining these spaces as one single project and one single building system. Yes.
The other thing that I have just about dunes and how they form with wind and sort of aerodynamics and all of that is looking at what happens sort of after this is built and what happens to the dune, to the sand, to the aerodynamics of the structure, and what happens sort of behind that structure, and if there's a way to sort of in the model, in the way that you're predicting how the structure is built, to somewhat inform down the road, how the dunes around this are affected, how the structure sort of has implications on sort of the future landscape.
We actually The intention is to have these pathways not only on the landscape, but also as a break for the movement of dunes. So as you spread the pathways around, you start to settle the dunes and the environment, so you don't have the effect of the moving dunes.
I think one of the obvious potentials of aerial architecture, and especially in the desert, is having the drone displace the formwork on which you build on top of, right? So you have this kind of fatalism going on. This is a dune. We sort of ejaculate on top of it, and that is going to be our structure. But there's lots and lots. I mean, you have this vast byproduct of displacing particles, right? So for the last 20 years, I've seen so many particle designs based on particle simulations. And now I think you have a fantastic, there is in the world no greater collection of particles you could shape than the desert, and you missed that opportunity. So do that the next time. What I think is it's just a natural byproduct, right? So why not harness all of this power? So sort of what I think is the quality of your proposition is the very impressive breadth of your work, right? You start by showing an understanding of the power of the technology, of the power of the proposition. You show simulations in terms of design, simulations in terms of the robot control. I work with a lot of industrial robots. I realize how easy it is to do in comparison to these highly dynamic robots. You've shown hardware, software development. What I think is very powerful about the proposition is how you go through these different scales, right? So especially the macro scale of your proposition, I think is very powerful, the desert greening. But when I see one of the last renderers in your presentation, maybe you can flip through the slide. I see, we see the interior of the building. It's that, the render, the last panel, the render in the middle, that one. But is this an architecture for people in the beginning? Because what I think is interesting about the desert greening, it's a kind of bootstrapping, right? Is that could you use this desert greening to, for instance, to plant rubber trees, such that you could sort of grow the binder locally? Metal is not the only reinforcement material that expands with the same coefficient as concrete. So can you grow your reinforcement bar, right? That's definitely a potential there. Finally, and this is a more general comment to a lot of it doesn't necessarily apply to your project, but the thing is that our architecture is essentially a technical culture, right? And you show a lot of technical capacity, for which I applaud you. But where is the culture, right? I mean, Archigram has done fantastic aerial architecture, but I specifically think of a project of Francis Alice, which sort of also hints at the missed opportunity of using the robots for displacing it. He did this fantastic project of displacing a mountain 10 centimeters in Lima, in Peru. So, that could sort of trigger this idea. But let's say 10 years ago, it was still quite exclusive in architecture to start, or 20 years ago, to do programming in this kind of technical development. But I think you also need to show a mastery on a more cultural level. Yeah, thanks.
I mean, just from my point of view, it's very, very impressive, particularly what we're looking at here, the series of models, the whole conceptualization of the site, the materiality, so many wonderful points. Of course, also the technical development. I appreciate this. Now, I think that's why I think it's a shame that, to some extent, some of the obvious points which you have put forward are letting us down a little bit in terms of the shape, the finding shape, and then maybe the reshaping into a more optimized shape. I mean, it seems to be there, but not been made explicit. And then the patterning of the reticulations and the structural logics behind them. So Why isn't, this could be compression shells mainly, then it becomes a problem of the foundational edge constraint. I could imagine that some of these path systems, that horizontal field you're creating, could deliver some of the horizontal constraints perhaps of these compression shells, but there is no awareness of, no talk about it. And when you look at this model here, the final rendered model, it seems to me that there is no much awareness at all of that. For instance, you would most probably run in the short direction, the primary direction of the reticulations, rather than in the long direction. I mean, I do like again that the squiggly line, which comes out of a natural sinus wave of the seemingly the result irregular, that you use that as a stratagem to through the stigmergy. It will not be it's very interesting what a line is in your system. I mean, you set it out as a line, but it becomes a kind of wavy line, and the second is placed on top. To work with that, make it explicit, analyze it, and then tease out the opportunities, but there needs to be a set of success criteria in terms of the structural understanding. The little bit minimal amount of structural theory needs to be implied and imposed, very, very importantly. And then also the language you're using. You're talking about a space frame. You want to build a space frame, which then seems to be requiring a lot of tension. But you start with domes, which is a very, very different system. Although, of course, you need a minimum of depth even there for irregular load conditions, etc. So this discourse, I think, is for me the biggest vacuum in the project. But it's all there available. I mean, you don't even have to do original research there. That's just getting yourselves up to speed. And then I think this is just incredibly striking project. I really find it amazing.
Yeah, I think they show I'll give this, they show the foundation and how at some point if this reconfigures itself, and sand will, no? But maybe that's the way in which you even bring sand out of the project, would be just the wind and would naturally happen. Then at some point it will find a very unstable condition, and probably that's a big issue to deal with. And I was thinking, is it the Pantheon that nobody really understood how it was built, and it was supposedly built through, it was like this. So it's interesting that this comes back many thousands of years later.
That's one final thing. So I have one question, which, when you started out the thing about the idea of building things with drones, I was thinking to myself, what can it do that you can't otherwise do? And that's what I thought was the most interesting question. And I'm not sure and maybe that wasn't the point of the exercise, but I think there is a question to ask. It seems to me there's a technique of building here that's never existed before. And so there is perhaps an architecture out of it that none of us even know right now. That's the question I wanted to ask.
For us,
I think a lot of these questions and comments I think I completely agree with. I think they're very good and astute. I do want to emphasize, of course, though, that some of the issues of structure and fiber alignment and things are valid, but I think it has to be recognized that what they're representing is what they've achieved technically, that there's not any magical kind of deceit going on or anything, so that those things that are easy to criticize are also the things that were perhaps less interesting for the research to focus on, knowing that those things are already achievable. So in that sense, one is really looking at a compression between a design and a construction process, and that's the emphasis of the thesis. And I think it also has to be commended that there is this tight loop between the idea of, like, the brief put the quadcopters and the 3D printing together. That's something that industry is supporting, and so is the government. So there's no real debate over that topic. But I think what they bring to the table is the understanding that if one is using autonomous robots, that one can go into a remote area and take the minimum of resources with them, and then use what is available and use it in such a way that you can then leave it to deteriorate and go back to the condition it was in before, and to understand that that's a temporal product that you produce, and that it can participate in kind of re-engineering the planet as well as providing an architectural output. I like the idea of the rubber plants in that sense too. I think that would be one great extension to the project. So on one hand, it's a technical project. On the other hand, it's potentially a scientific or political project as well.
But I mean, it doesn't succeed or fail in those comments. No. At all. It's incredibly, I mean, you said inventive. That's what it is. It's seriously inventive. And so it's really just saying, these other things, these technical inputs, they're all things that will carry on and you'll do. And you can get, you know, there's a huge amount of work to be done, but what it is the potential for it. That's what's incredible, is the potential. So please, if it appeared critical, it was not critical. It's just saying these are things you will need and will look at, and it will inform the way it develops. And I think for me that you know, that's what's exciting about it, is it will develop.
Architecture as a machine, right? And could maybe, let's say, I mean, the architectural proposition we see here is like the scale of a sports hall, but your idea is so lucid that maybe that architectural scale is maybe not even ambitious enough for what you are putting forward. So this could be a machine for desert greening, right? And I think by a few simple means you could make the proposition more concrete. I mean, what's interesting there is you have lots of particles and an insane amount of energy, right? So by a simple question like 10 meters of solar panel would empower how many drones, right? And so that you could excavate a certain area, or you could get a certain body of work done with how many robots powered by how many panels, right? And that's quite simply you could sort of hypothesize the macro proposition even more concretely. Yeah, I think that would be fun to see.
Can you just tell me how this happens with the greening, or what the domes or the systems deliver towards the greening?
The idea is that remotely the deserts in general will be constantly being monitored, and when you identify a potential area for greening, which is water and the oasis, it can send this system there remotely and autonomously to start constructing the structure, trying to create an environment that is more suitable for greening. We have developed a few strategies that we didn't have enough time in the research. Like, we start developing in the late moments of the research. But our idea would be to, with the rovers, start channeling this water from the oasis, so we can create this pathwork that would distribute the water throughout the system, and also have these pathworks breaking the dunes movement to create a scenario that is more stable for the plantations. And what else?
When it comes to the applications and this kind of thing, I think there's a moment where you can stand back from the research and see what opportunities in that environment you have, right? There is an increasing desertification. It could be a different attitude towards creating structures for that. So I think, I'm not sure that this is really the ambition to make these kind of pavilions in the desert. There are opportunities to really create different kinds of architectures that actually maybe have more protective characteristics or other aspects of things. The architectural problem, I think, is an open one. And I think that this is the beginning of that kind of exploration. There is also a certain sensitivity to the actual materiality of things. So I think, honestly, there's a hydration aspect to maintain this kind of dune formations. Otherwise, you're always going to be looking for something that has spatial characteristics, but this is always an evolving formational kind of landscape. There are a lot of challenges, and I don't think it undermines the project right now at all. I think it's really for you to look at the service, I think, of the questions of what architectural possibilities are in a much more expanded field, if I'm honest, and actually start to see where this kind of work could situate itself so it continues. I mean, at the end of the day, I think it's more than just sand printing. So I think that that objective now for you is to be kind of creative in trying to identify terrains and speculations that are not just speculative for the sake of speculation, or responding, for example, of digging trenches to get water because that's how your system works, but really is trying to foster, I think, a very different sort of approach, and almost like a surgeon kind of identifying a problem where this thing can take the next steps to develop. Like that's part of your next 2.5 weeks of self-reflection, but it's also potentially, in what we hope anyway, the beginning of a career, which doesn't necessarily mean entering into an office, and trying to find, I think, the mechanisms to enable you to do that. This isn't architecture in a conventional sense, so you have to somehow have the accountability to formulate and to be very explicit and precise, actually, what is it that you're really working on. I'm not necessarily sure you have that moment of reflection yet. I think it's natural that you've gone through a process, but I think it's very imperative that you take that opportunity to figure out the possibilities of what it can be. You know, I don't think that you need to focus too much on some of these visualizations. They are a version. So I think, you know, keep an open mind about that stuff, and I think that that's how you should continue to pursue your thinking about it. You've built an understanding, and there's a world of a lot of very complex problems out there, and you should identify things that you feel are ways that really could be thought about in a radically different way through a system like this.
I think what the project does is make us think of architecture engaging with something that is not the city. And I think we have been used to think about cities and buildings in a way for a long time, and we haven't thought about rural or desertic places in a long time. It seems like it's actually a place for possibilities, and clearly this is a technical problem in many ways, but if you just think of what this doesn't deal with, which is what we're used to deal with, which is building, I think it opens up a lot of issues of, again, precision, materiality, space, even if this is for human or not, which probably is not the case. And I think it would have tons of possibilities not thinking of this as being a building. And my sense is that this is where maybe there is less pressure for architects to work with. There is less pressure of history, less pressure of paths that we know how they work, and therefore there is a bit more innovation actually. In this, there is much more that is possible.
Yes, from my side, I'm coming from the industrial side and dealing since years with flying objects. I can say that probably in the near future we will be able to have self-localization with these kind of robots. We have probably energy enough, or also you have these cable in your first version. So it also would be possible to bring external energy to the whole system. So I think, yes, it will be possible. What I didn't got in your presentation is why you need the rover. And I think actually this was a missing point which I didn't understand, and where I also think you should go a little more in detail about the printing process with sand and water, and how stable the structure can be, and if you really print layer-wise, or if you maybe in the end print more like we already can see over here. So then maybe you don't need the rover anymore, because this is something in my mind it doesn't come together with the flying drones on the one hand, and then having these rovers just going over the almost the first layer of the structure. So yes, I think you did already quite a lot of research, as I've seen what is technically possible so far in robotics, but probably there's even much more possible soon. And I think you don't need the rovers. Your task mainly would be how to develop the printing part, actually, using sand, finding parameters to generate structures that are really give you the opportunity to build all kind of things with that.
Yeah, thank you guys. Well done.
all, guys.
Thank you.
Yeah.
Thank you.
Is this yours?
Yes.
Thank you.
Oh, I didn't see. Can I put this?
Yeah, sure. Thank you. Is it switched off? Not playing. I don't know. Ludo, can you ask him if the screen? I don't know if the screen is switched. No, yeah.
Yeah, you can ask them.
No, they bring. I doubt they will fit. Thank you. Thank you.
Anything.
Okay, guys, we're going to start. Thank you.
Good afternoon. We are from Sharjah Bhushan Studio. My name is Laura, this is Ramsey, and that's Aditya. We are going to present the research on material and fabrication method developed to analyze the possibilities and limitation of scale-up the 3D printing technology to transform the way livable spaces and design are produced. Nowadays, investigation in the field are revolutionizing the conventional architecture and construction process.
The studio research agenda explores the use of combined technologies, robotic arms, and 3D printing in the architectural design process. The main objective is to translate structurally motivated spatial networks into habitable dwellings. This can be achieved by integrating digital fabrication into the design and production process. Along the lines of Joris Laman studies, this dissertation analyzes how spatial printing can define a new design and fabrication method that addresses new formal and tectonic challenges with spatial extrusion through the understanding of material behavior. The conventional approach of layer-by-layer printing method is replaced by spatial extrusion. Thus, it is essential to design a 3D printer technology and define a particular external digital control system. This will be achieved through the customization of existing industrial robotic arm technology responding to the material's properties. In this direction, the research continues the following steps. First, research on material properties and behavior will be developed, focusing on existing 3D printing filaments in the market. A wide range of 3D printing filaments can be found from thermoplastics to composite material. They are characterized by their phase change behavior and scalability. Looking at the tool, after industrial robotic arms will be studied, personalizing them through the design of an end effector. The potential and limitations of this technology will be investigated to set up design strategies using spatial printing. Industrial robotic arms have an inherent control that ensures precision and quality. Finally, the design process will aim to find the optimum geometry based on material behavior. These geometries should ensure the structural stability throughout the printing process, with the minimum use of temporal supports and material. Moving forward, looking at the precedents, previous researchers on this topic were analyzed to draw conclusions on the premises and research gaps existing in the investigation on materials and robotic technologies. These projects were studied to offer a better understanding of this printing system and establish a research procedure. The analysis focused on how the material behaved and how they were used, how robotics were customized, and how this was translated into spatial printing. The advantage and constraints that this extrusion method offered were identified. Programmable material. The investigation aims to develop the potentiality in the architectural field of existing 3D printing filament available in the market. PLA plastic was chosen due to its physical and chemical properties. It is malleable material which can be easily repaired, bended, and welded when heated. Once this material is engineered, new physical properties characterized it, offering further advantages and the capability to create structural networks. In order to comprehend the material behavior and properties, multiple tests and experiments were undertaken. First, the material was extruded using a single nozzle manual extruder along a vertical axis, as shown. The objective was to find out how to control the heating temperature, avoiding cooling agents. The yellow line shows the time of extrusion required depending on the cooling agent employed. High extrusion time with same cooling system resulted in thicker strands. Moreover, a multi-nozzle manual extruder was used to find out how the resolution of the strands extruded could be improved by twisting the material. As shown, the material output depends on the time of extrusion and the heat and rotation control. Nevertheless, it was concluded that manual extruder do not allow an effective heat control, and therefore the outcome was not precise and did not ensure stability and strength. Therefore, multiple prototypes were designed, improving the control over the different parameters and hence getting a better output. The multi-nozzle extruder version 2 offers a better temperature control and therefore higher control over the final output. The multi-nozzle version 2 can provide different outcomes, changing the extrusion method. The free flow extrusion means extruding the material with no tension applied. As a result, a random twist is obtained with no strength or stability to allow spatial printing. When extruding under tension, the 4 filaments are twisted together, and outcome is a single strand with higher strength and stability. Last is the linear tension, which means extruding under tension but without twisting the nozzles. The different filaments can be identified, and it needs for a secondary structure to get the shape desired. While extruding under tension can be employed for the main members of the structure, and linear extrusion can be used for bracing when it is required. 3 different tests were conducted for this aim, the first animation shows a one strand of 3 filaments extruded with multi-nozzle version 2 extruder compared to the second image, which is one thicker strand, 15 filaments. No difference between both deformation can be appreciated. Furthermore, the last animation shows the bending of 3 individual strands of 3 filaments each, which are connected in the extremes, showing the unpredictability of the deformation when the strands are not connected.
Moving on to the material behavior, the next step was to study how a network of strands respond to different bending strategies in order to obtain the form that responds to the structural and aesthetic requirement. Active bending was one of the first strategies that we studied. This means applying a force to a network of elements that have been previously 3D printed. Once the force is applied, the resultant form is braced to create a stable structure. The bracing needed is established through simulation. The digital speculation shows the red parts where bracing will be required. The same strategy was tested along x-axis to explore the better response. Nevertheless, with bending strategies, the structure resultant was not stable as required.
I'm sorry for the interruption. PowerPoint has crashed.
We are really sorry about that. So the same strategy was tested along x-axis to explore which could give a better response. Nonetheless, with bending strategies, the structure resultant was not stable as required. So the second strategy that we explored was gradual bend and brace. The figures displayed in this slide show the result of gradual bend and brace strategy. This involves printing every member strand, bending the individual item, and once desired the form is obtained, this strand can be braced to the one before. As a result, the stable and strong structure is obtained. This method allows the creation of positive curvature elements where the structure works in compression, while negative curvature elements that work under tension. The structural engineers explained that the PLA plastic that we're using works better under tension than compression. Therefore, this dissertation should pursue the design of structural elements with negative curvature. The third type that we explored was tension bending. The tension bending strategy set a number of constraints to control the bending material, optimizing the tensile property. In order to improve the overall strength, the bracing required generates a compression network that improves the resistance. Getting on to the analysis based on these different types of bending, the illustrations show the different bending strategies. The yellow line shows the level of deflection, the red shows the quantity of bracing required, and the blue represents the complexity of robotic choreography. The tension bending seems to be the most suitable to employ as it requires less robots, the most stable form during the process of construction, and needs less bracing. Therefore less material. The bending of different strands are easy to predict as constraints are established. These constraints have to be studied in order to optimize the use of material while creating negative curvature that satisfy the strength and aesthetic requirement. The digital studies show the number and the position of constraint modify the curvature of these elements. The compression network previously mentioned has a great impact on the strength of the structure. The video shows the loading test developed to analyze two bracing solutions, the linear and cross. As it can be seen, the first one fails due to the failure of these nodes. The second one is more stable because it's a continuous print. Different bracing strategies were studied comparing the deflection amount and the amount of bracing required and the printing time needed. The best solution is the spline bracing as it deforms less and requires less bracing and printing time.
As mentioned previously, the incorporation of robotic arm in the technology allows to scale up 3D printing technology, incorporating in the architecture process. Understanding the robotic tools is essential to create design that offers innovative solution. First, the arm reach should be studied to identify the limitation of that tool and define solutions that allows the creation of large structures if required. For the customization of industrial robotic arm, it is essential to design the end effector that allows the extrusion of the material following the requirements of resolution, time of printing, and resistance previously explained. Furthermore, this robotic technology should be controlled through computation data. The end effector design is designed as a multiple nozzle extruder of 4 filament. It has 4-step motors that control the printing speed and twisting of the material. It is designed to print at any angle in space and with 3 different extrusion methods previously explained. Tests were undertaken to understand how the robotic arm could be used to translate the visual into physical model. At the micro scale, the printing speed was tested to define the accurate tension for printing that offer a good resolution of the material output. On the other hand, the macro scale the printing process was examined. The sequence of printing should be established based on the network of tension bending to ensure the stability of structure during the printing process. Physical and virtual model can be different due to the multiple factors that affect the printing process. The difference can be defined by scanning using feedback loop. Printing tests were conducted in Odico to find the equilibrium between the printing speed and speed of the robotic arm to get the desired resolution. The images show the speed test developed. The control of the speed ensured the consistency of the resolution of the material. The video shows the sequence of printing before explained. A series of primary members are printed using temporary supports following the constraints that control the negative curvature of the elements.
Looking at the feedback loop, for the feedback loop, it is essential to design an end effector that can scan the physical geometry to compare to the digital simulation. This end effector is a single nozzle extruder designed for Nachi robot. The scanning and extrusion is controlled using a proximity sensor and an Arduino board. To incorporate the compression network, it is important to detect the displacement between the digital and the physical points that configure the element. For this, the physical model is scanned based on the digital geometry to remap the virtual points based on the physical reality. It was observed that the maximum displacement registered was 3 to 4 centimeters. This video shows the scanning and remapping of the points for the printing of bracing networks. Robotic fabrication. A system of printing is based on a conventional robotic fabrication process, placing the robots in a cell space based on a robotic reach, using multiple robots that could be placed on rails to add one more axis. This will allow the fabrication of larger scale elements in more effective way. The different cell arrangements were studied to find how to use multiple robots could be combined in fabrication process. This visualization of production unit that uses 3 robotic arms are placed on rails on the floor. The dimension of the cell is 20 meters by 6 meters, but defined considering the maximum reach of the robotic arm. Based on taking into account all the previous research, the material behavior and the robotic fabrication, a prototype was designed. A network of printing process was based on the material behavior. By superimposing the printed elements, the base branches out into multiple connections. The video shows the sequence of how the prototype is printed. Bundling was employed to allow the branching out of a single base structure. This technique increases the cross-section at the base component, enhancing the stability during the print process and leading the structure that admits to further spanning. These images show the prototype model and showing the network and the complexity of the form.
Moving further, the design approach is a form finding process based on a material behavior, physical models, and digital simulations. The individual tension bending elements previously explained define a structure when they are printed together using bundling. The first structural item that was studied was the arch, due to the fact that an aggregation of arches creates space. The cross-section of the individual elements will define the proportions and characteristics of the arch, and therefore the space. For example, these fluid networks presented are as a result of aggregated arches. These networks, when connected together, can be used as a form-finding process. Looping structures are another result of the aggregation of arch. As explained previously, the dimensions, proportions, and characteristics modify considerably the conditions of the indoor spaces. On the other hand, as shown in the prototype design, using bundling to span in different directions results in a multiple branching option. The horizontal or spatial network of these structural connections can be used to define spaces. Some of the examples of these spatial solutions were developed. Furthermore, the technology studied allows not only the design and fabrication of structural elements, but also the creation of surfaces. This is achieved by the linear aggregation of the tension bending elements. The layered printing covering the individual elements result in a skin that provides different atmospheric conditions by controlling its porosity. The target is to apply all the concepts developed through the material, robotic, and computational design research for the design of a dwelling. These case studies in the history of plastic architectures looked upon how each of the units are built, connected, and extended, which allows a symmetric way of expansion in the future. Open planning, different type of interconnection expansions are the key features of our design development. The process shows the geometric evolution and the form-finding process, a sequence of steps developed to achieve the geometrical possibilities. Using a unit as a form-finding module, the images show how we can apply our structural system based on material behavior. The process of layer printing is used to create a surface as explained previously. The deflection analysis shows the area where the surface density needs to be maximized, and aggregation of these individual modular units results in the form of finding process. The video shows the printing process and the assembly of a single modular unit, considering all the points that were developed throughout the research. The structure based on tension bending property of the material. Printing process uses bundling, the surface generation, and the assembly of all these units, and also the flooring, as you can see in the video. Moving forward, further application of this system shows how an individual space is formed in different iterations of it. The forms are more singular and free-flowing, and also has the possibility of expansion as the openings are modular. This is how we look at a space. Thank you.
Negative curvature, also bracing, and surface studies. This is the tension model where we add the bracing, and here's another model that tension model but without bracing, and here's our geometry generation. Here's our single nozzle extruder using the doodle pen and the sensors. In the beginning, we tested different materials, and for each material, we built the factor. So this one was for UV resin, where we had 6 UV pens. This was for the clay, and then we started with a single nozzle, testing the PLA. We went to multiple. This is the first version of our multi-nozzle extruder, and this is the final product. Here's some of the connections, our structure. Here's the node studies we did, and some of the units orientation forms. And here's more, and this is the active bending geometry, and this is our final prototype. Further, we have some of the studies, early studies of nodes and forms, and this is our initial study of bundling. Thank you.
Am I right in understanding that you've arrived at a kind of module, and that module goes on to create all these, these are then kind of smaller versions of which is built up from one. And that's one example where you combine those modules, a triangular version rather than a square version.
Thing is, for expansion, you need to bundle it. It needs to be a continuous trend. So for expansion, you always start at the base so that you can expand more. So the base will become stronger. Even though it looks like module, because the tension bending is at an individual section, but the printing is always continuous. So as you expand further, you always start at the base. So, but the tension bending is seen in particular sections.
What is tension bending?
The thing is, the material that is being printed has it does not have any compression or bending resistance, but it has a tensile property. When it's printed, it tends to pull the primary members towards each other. So, and that's how we achieve a negative curvature instead of adding some external force, which is active bending. When you have a network and it's being popped up.
What she's asking, I think, and it's something that I wanted to ask, but it's quite difficult. Because what you're talking about is when you take a member and you bend it, you induce free stress. But this expression tension bending is really not the right expression, right? Because any structure like this, this is in compression. You push it, it's in compression. It's standing on its own self-weight in compression. When you turn it on its side like that one, that's in bending. But the top face of it, and you can do it, if you hold a weight, the top of your arm is in tension, the bottom is in compression. That's the way a cantilever works. It's a very simple thing. You always have in a bending element both tension and compression. So the expression tension bending is slightly misleading.
That's why it becomes a process notion. That's what I understand now. It's just, but I have another question about this because you seem to have this negative curvature, which makes sense because it needs to be, these are thin elements, curvature of one kind or another, and that makes sense to me. Then you have these moments, the next module comes in. At that moment, I wonder what happens. First of all, these surfaces between these negative, they need to pick up compression, of course, because that's where it goes, right? But then here, what prevents us from pulling apart? There needs to be something here, although it looks nice empty. There you get an inverse. The compression tends into a pushing outwards. Then would have to have tension elements to hold that.
I would suggest that there's a kind of level of investigation at the beginning to the process. First of all, this idea of this rotating, the thing you've got very slender member, and you use the multiple nozzles to create a bigger diameter. That's quite a good step. That was a clever step to do. But what for me is missing is early investigations into what buckling is, what compression is, what tension is, and how you've arrived at what to me is a very, if you don't mind saying, slightly mannered element. I don't really quite understand why you created it like that. I mean, I'm sure you can explain, but you know these chords and these rather graceful curves. It seems to me, if you're investigating a structural thing, which is a combination of materials to create larger structures, as you're going on to do that there are some simple pieces of work on testing things, just showing what buckles and what doesn't buckle and why. And I would have...
the webbing here. Pick up the compression.
Can I ask, because this thing is being streamed and people are listening abroad, could we use a microphone just so those pop up?
So there's a kind of irony is that your your ability to print in space is based on topology, right? You are combining multiple strands. Weaving is sort of the leading idea there. And sort of Neil's critique is about essentially topology, right? So here you are sort of faking these nodes by, you know, coupling them together after the fabrication. So I think if you succeed into sort of making this a topological operation, like weaving this together, it would be, you know, a more elegant manufacturing process and structurally much more sound.
It would also make, I think that suggestion, I was thinking of something similar, and I you know, it always happens when cable ties appear in a model, like everybody just stares at the cable ties. And we understand what it stands for, which is that there isn't just a proximity of two elements, but somehow there would be a transferal of forces. And of course, the great potential in your world, it seems, is that the idea of a joint or a web, or, you know, those things coming together, is just part of a spectrum of bundling that's happening throughout the system. So it seems like it's more than just a model-making mistake. It's a sort of theoretical or conceptual habit that somehow the joint is going to be different than the elements of the material. That'd be maybe one thing to point out. The feature that seems really striking, and compared to, let's say, the presumed horizontality of the sand dunes we were just looking at, is the potential, weirdly, for the most vertical architecture imaginable. Right? I mean, this is a bundling that has no limitation in that your raw material is just however big the spool is. And it's not that it could just go, you know, like a test, you know, version 1.0 could be, how can I make the radio mast that the world is building right now in a totally electrified world in which signals are being sent around the surface of the Earth? Man, you've got a perfect architecture, it seems, for that, because just the bigger the loop, the taller this machine can become. And if you go back to a century ago in the building of radio masts when steel is industrialized, it seems like there's already a deep history. But the other way, if you're going to go to the and it's almost like a default DRL decision always to make a pavilion. You know, at all cost, our architecture will first be a pavilion, and it will then conquer the world. And you know, you gotta, I don't think that's a problem. I mean, Mies made it work pretty well. I mean, there's a habit that could be engineered into it, but it seems like then your pavilion would be one in which, again, because of the continuity material, could span tremendous distance compared to the rolling of industrial elements right now that have reasonable limitation. Yours, with robots on site, could be bundling things that are spanning tremendous distances and operate with a completely different kind of interior than that sort of familiar scale. I think the final point I was thinking about as you were showing those beautiful machines like this is there's something in the history of rope making that would be valuable in that the bundling of material in one direction, which happens with the strands that make a rope, to give us enough elements in which then energy is reversed and those strands are wound around one another, creates the possibility, it seems, for not just a stiff material, but also a very supple and loose one, which is what rope making ends up doing to material. It also introduces the possibility of discontinuity in the dimension lengthwise, which is what furling and those kind of techniques used by rope makers allow. The element doesn't need to have the same dimension along its length because we can wind more materials into it or out of it, which again seems like a tremendous advance over the idea that those things have to be a sort of stable element that somehow just interacts with other uniform materials. But I think overall an incredibly interesting sort of first step in trying to imagine how these machines can be used to almost invest energy into the material more than just find form with them. And that seems what the twisting material is doing more than anything.
I think if I can pick up on that, the effort is in the research and the material is really commendable. But what I think is novel in the area of 3D printing is to combine the efficacy or the expeditiousness of forming larger structures, not by layer by printing, but actually using its capacity to be formed while it is being printed, and therefore also has a capacity to learn from the rope making and other ways where the form is actively arrived at in a kind of incremental way. So I do think that there is a lot of potential there to investigate how it corresponds with like traditional craft as well in rope making or other grading strategies.
Industrial knitting, all of those kind of. But why do you guys call it printing? I mean, that is, like, as an outside critic, I don't get it. Like, what is being printed other than these sheets? Like, there isn't anything in that conceptual framework, and it seems like that's exactly what you're trying to challenge, that instead of a particle-based finite material, that it's actually the investment of energy, literally the energy of twisting into a material that gives you the basis for assembling a figure. Why are you calling it printing? I mean, you don't even have a 3D printer involved, do you?
It's just the 3D printing filament that's being used, but...
Where?
The nozzles,
That have been converted into the stuff that feeds the material in, the line into the...
because the printers also use the rounded filament, plastic strands. So there's certain analogies. But it's much more at the same time.
Is there a version of it you can that you've been able to print the whole structure? Oh, print wrong. Weave, knit the whole structure coming out. Have you done that? Because this is, you know, the strands expand.
The lower section of that prototype was built
Fully knitted. Because that's the key. This thing about the clips, you know, that's what you want to do, is knit the whole structure as one. That would be fantastic.
Printing filament, like there's the additional advantage that by heating it you can fuse the material, which like regular braided ones is relying a lot on friction. This has the capacity to have both friction and like you can fuse material as you go.
Yeah, I mean, we're talking about tension, but really this material is resistant in compression, is plastic, and it's heated, and then it also gets cooled down and has stress in itself, so it's actually quite resistant per se. It's not just like a rope, and I think it's much more potential that way. Are you happy of the way in which it looks? I mean, it clearly is performing well, but I think that's the second question is, there is this idea of the structural system being leading the design decision and the aesthetic decision, and there is this Calatrava, almost contemporary Calatrava look into the project, the pavilion, yes, being a question. And I think what is the ambition to move it beyond the naturalistic, biologic, or not, or that is where it stands, and that's what will be always leading this research.
We use this material as a proxy material, but this material can be developed more, or any other 3D printing filament that can be wood-based or carbon fiber-based can be introduced, and like even the resolution can be changed based on the intelligence of the machine. So like this is the first prototype, but it can be further developed over a period of time, and the fact that it has the temperature is controlled to such an extent that it can print, like the result is like quite immediate. So, and that's what we also wanted to look into other materials that can be developed, but the geometry, like it can be explored more, but we can see that.
I don't think it's an issue of material, because I think you don't need to substitute material. You've taken on board, and I think commendably, this aspect of reintroducing plastics in architecture. And of course, that had its heyday in the 60s and 70s, and how to reintroduce that in a meaningful way is something that you have to, I think, continue to work through. The part of the project which I kind of feel quite close to is your interest in sort of building these machines. And I think that part is interesting. Your exploration and conceptualization, I think you should expand some aspects of this, because if it's always talked about in the domain of just printing or in the domain of the robotic arm, it's another robotic arm or another printing project. And yes, we can make it legitimate that people are throwing money at this, but to be honest with you, it doesn't interest me at all. For me, conceptually, your project is super exciting, because you could conceptualize space making as a continuous line, and your structure, your printing process, all of those things actually really take home when this is a continuous kind of strategy. Where it starts to become problematic and falls into a trap, I think, when you start to make these things as discrete components that need to be assembled. So the conceptual speculation should be really about thinking about that continuous line and thinking about, especially since you're working in the domain of housing, how that scale actually allows you to really think about it as a continuously kind of, not just a woven piece, but something that has features and attributes that are radically different. I don't think you need to think about carbon fiber or this is a proxy material. I think you should try to expand because you've designed an instrument and you have the capacity to simulate it. Does it have to be so discrete in the way that you're showing it? What I really like about the nozzle is also these kind of random curlings and furls. There are different kinds of attributes of how you could deposit this line in space and what a connection is, not a joint actually. It's like this fantasy that Conrad Waxman had and people like Le Ricolet to be in the space of a rope. These are the things that preoccupied these guys. Some of the most interesting projects were speculations of this kind of inaccessible. You build these kind of tools, give you the legibility to be able to speculate on those problems. And I think that's where I think you should start to expand things. I'm not necessarily sure this is about Proto-Calatrava 2.0. I'm not necessarily sure that this should be a default DRL Pavilion 15.0. It is an issue of your conceptualization of space making through the instrumentalization of your process. And I think you've always kind of wrestled with it, but you've never felt comfortable of just saying, you know, fuck it, let the machine keep spooling. Let it see how it can continuously work. What is our limits of constraints of this choreography of the multiple robots kind of allowing us a certain thing where this singular line would actually have to be continuously played with, you know, like a bunch of kittens with spools. Like, this would have a very playful dimension, but I think would also address this kind of overly kind of simplified version of what an engineering aspect of such a small architecture would be like. I think that would just liberate you in a way that I think would be really useful.
I mean, it seems like you need in that sense, though, to declare the project more upfront. I mean, you're asking them to declare a project that this gets aimed towards. And as I understand the DRL studio, for the most part, the declaration of the project is what are the technologies we're going to experiment with that might then lead to speculating on the project, in which something less familiar than a pavilion might be aimed at. But if you were to say, for example, we live in an era of the world's tallest buildings, almost unimaginably slender, even for 10, 15 years ago. I just visited a site in New York that's 27 feet high that will be taller than any site in the city in 5 years' time. It's unimaginable that that could happen. You know, in a room that's half the width of this hallway is going to be taller than anything in Manhattan. It's possible because of high-strength concretes, a reduction of steel such that the dead loads, etc. It seems like you're working with the kind of thing that could immediately let us think of those kind of problems in a completely different way. And I don't think those are necessarily things that come afterwards. In a way, they would ground beautifully the potential of these kind of projects, right? In which these machines would climb up into the sky and twist this stuff to the heavens if you want. I mean, it seems like what you would be doing is showing how low the Earth is rather than, you know, how tall. But it would be up to you, I think, to claim that territory before somebody else takes the work at a technical level and starts to imagine where might it lead. It seems like you would want to do some of that work too.
Yeah, and the technical continuation of the project, I think, is important. I really disagree with Theo that plastics is maybe the way to go. I mean, imagine that you would weave this out of steel, right? What was a bit clumsy in the project was some of the support structures, right? If that is a steel plate, you can just continue to weld it together, and then the temporary support structure is inherent part of the overall structure. This is PLA. It's very expensive, right? So it's very clever to do the prototyping in that because it's an easy material that is very easy to work with. So you dodge the problem of having to figure out how to weld this. But metal's cheap, right? Dirt cheap. And then the thing is that if you do it in metal, you could apply it to tomorrow as rebar, right? Rebar for complex concrete structures, or actually do the same thing in balsa wood, right? And you so do it on a maybe architecturally less ambitious level, but that you can start to supply an industry, such that you carve out a space that you can give yourself 5 years for continuing to develop this. And I would really encourage you to do so. But you gotta resolve the problem of coming to terms with topology. This is really essential for advancing your fabrication issue. It's very key.
To a reference you had in the project, in the presentation, and in relation to your brief on housing. You had Cheniak, and you showed his polyvalent cells, right? And I think this is an interesting, Cheniak, I am a big fan of Cheniak, actually. I think he was really ahead of his time. But particularly, there's a clear relationship in Cheniak's work to the opportunities of architectural space and the ability to add spaces over time in relation to production process. So it makes sense that Cheniak's polyvalent cells are prefabricated. It makes sense that because they're prefabricated, they're modular, because he's doing fiberglass and sometimes plastics, but mainly fiberglass. And so here you have a casting process where it makes sense that they're all the same module because he wants to reuse the formwork. The other thing is he explored it not just as kind of pavilions or houses, but he also looked at multi-story buildings and also adding cells to the outside of existing buildings. So there was an exploration of the potential of his concepts to be infiltrating different areas of let's say the architectural use or this kind of thing, and over time. And I think this is something that you can take up between now and when you finish your book, because at the moment, your final proposal is surprisingly a kind of version of Cheniak, right? You have a modular cell, and this is where I kind of want to go back to Theo's comment as well. I do think that your potential lies in more continuous material where you differentiate the material across the scale of the architecture, not at the scale of a single room, and that can really start to impact also a spatial strategy. At the moment, there's no spatial strategy that corresponds. Like, the whole project's communicated through a structural language, but your brief is also looking at housing, and I think you need to kind of re-look at what is different between what you're doing and what Cheniak's doing, and the biggest difference is you don't have formwork, you have a very inventive process, and that process enables you to do a different thing 1 second to what you did the second before. You don't have to repeat what you've been doing. And so one would expect that there'd be less repetition in the architecture, and potentially something that I'm very interested and fascinated in your project is the hierarchy of the threads and their distribution. Like, this model's super interesting. And I would imagine that the architectural space could start to relate to the structural organization too. So for instance, the trade-offs that architecture needs to have become interesting design problems. So I need a lot of thickness and density material for structure, but if I want windows, I need maximum porosity. So how do you negotiate these things becomes where I think the project wants to be.
I think the project wants to be an infrastructural project. I think it's very, is this screaming for an application that is, because it's structural and it tries to use the material in its basic behavior, it does what a lot of infrastructure does, answers a structural concern, and not necessarily a programmatic one, or not yet. And I think that's always a struggle, and I think I mentioned Calatrava because I think that's, in many ways, there are incredible achievements in his work, but also there is this difficulties in applying an architectural project to a structural system that has a purity in the way in which it's constructed, doesn't allow for hybridity, doesn't work as well when you start actually working in architectural terms. And this has to probably struggle with the same problems when it's such a pure system and follows structural concerns at first.
I think like it was perhaps applies across the DRL, like for technically capable architects. Like, I think it's almost a responsibility to convert or show the way, a pathway from converting instrumental knowledge into design knowledge, so that in that sense, like, I'm not sure, so more in alignment with what Theo was saying, that like, how do you take all of this knowledge of making machines, and how do you make it operational in a kind of design sense, like, so without being overly burdened by the technological aspect. So in that sense, so the housing in our mind was a way to provide a context in which that can play out, as opposed to only tackling a kind of infrastructural project, which this seems to be more amenable to in the kind of technological aspects.
Thanks.
So I think we're going to leave it here. We're going to take 45 minutes break, grab some lunch. You guys can go and grab lunch as well, and we'll pick it up tomorrow.
Thank you.
Boom, boom, boom. There you go. 1, 2. Do, 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 do.
New batteries in this one now. It seems full on this.
Hello. based on developing a reconfigurable and self-structuring system that is capable of mobility and interaction for the purpose of creating dynamic and adaptive ecologies. By looking at a colony of ants, we tried to understand their collective behavior and their capacity for collective collaboration. We found it particularly interesting how they could transform into becoming an infrastructure for themselves and emerge as a single entity for accomplishing complex tasks. Moving on, our research is influenced by the works of Carl Sims' Evolutionary Creatures that demonstrate the usefulness of developing a novel system, employing learning strategies and evolving mechanisms, and simulating behaviors virtually to achieve specific goals. We looked at NASA's TET robotics to help us in the development of a robust model capable of mobility to overcome obstacles and difficult terrain. Lastly, the work of Hot-Lipson's cube served as an ideal example for understanding self-assembly and self-structuring. Our initial research developed around investigating systems that are capable of storing energy and simultaneously transforming their geometry. For this purpose, we built and explored a series of study models that were a combination of soft nodes and rigid connecting members and vice versa. Through their deformation, they could adapt and a single unit could connect to other units. So at the first iteration at the prototypical level, it consisted of a tetrahedral geometry which was composed of pneumatic connecting members that could be actuated in a sequence to produce mobility and also other behaviors, along with connecting to other units through their nodes to form complex body plans.
We are trying to build a simulation system for these robots to be controlled by a learning system. We are trying to make the system adaptive and with these robots autonomous. And the most crucial part for the autonomy is learning. And this is a genetic algorithm that tries to calculate an actuation sequence for these units. And you are seeing a simulation that runs to calculate the maximum distance can be achieved by minimum actuation for a body. We started to test multiple scales of bodies, and we realized that as the body became more and more complex, the computation time became longer and longer. We started looking at a knowledge distribution system in order to distribute this computation process through a larger crowd, and started looking at interaction systems and basic rules and how these simple interactions could achieve a complex network formation. Besides the network formations, we also started looking at the deformation of these units, and we looked at how these relations could start to generate spatial formations and structural formations. Here you see the growth strategy applied based on different tasks. Sorry, just a second. Can be open. It's wrong.
That's a hybrid.
Okay. Yes. This is an input in our learning strategy.
From the initial studies, we were able to generate these stick models. That helped us to analyze an actuation pattern in the tetrahedron.
Yes.
Now it works. Okay. So, moving on to the transition, the deformation strategies that we learned from the tetrahedron were used to create a chain link system that is capable of transformation, creating different states. It is also able to have a stronger joint strategy, making it efficient and stable at different geometrical configurations. So the the unit created by us had three major states of mobility and self-structuring. The closed state of mobility and self-structuring, the flat state of self-structuring, and the open state of both mobility and self-structuring. After understanding the unit at a single level, we started evaluating multiple unit configuration with the same unit of transformations. On a prototypical point of view, the experiment started with first achieving mobility and transformation. So initially the transformation state, we started with the transformation state that is going from the flat state to a closed state. This was achieved by actuating the link pistons that are in the prototype, where that closes one by one, first creating the flat state, and after creating the flat state, it actuates the surface to create a more accurate connection module that is created by an electromagnetic piston and a rod, which makes the fifth hinge work. When we talk about closed state, it's the best for creating mobility because of its rolling motion. This is created by continuously transforming, changing the surface pattern, creating a disturbance in the center of gravity and making it roll, which can be quite helpful in not only flat terrains, but in rough terrains as well. When we talk about the open state has two main functions, the straight movement and the turning movement. So the main actuation is created by the first segment anchoring, the three segments extending, and the other segment anchoring, and vice versa, in both the systems. In the straight system, both the surface pistons are getting actuated. In the turning system, only one side of the pistons are getting actuated. So in the surface system, in the straight system also, you have an open flange and a closed flange. So the opportunity the open flange gives you is, it's more stable, and if it's a smooth surface, it moves through it very nicely. When you close the flanges, it gives you a better anchorage at the point, which helps you in an aspect of climbing terrains, which have a bit of altitude, like an angle. The twisting motion that we were able to evaluate helped us to achieve that turn that we were looking for. Continuous actuation of these anchor, extension, and anchor helps us to create the turn. After looking at the single prototype, we looked at multiple of them able to climb each other in order for transformation, like self-structuring to happen. This is one of the examples that we were able to achieve, one bot climbing the other. Okay, go back. The system that we are using right now is a pneumatic system, which is divided into 5 segments, equally distributing the pressures in all 5 segments, and with the center segment being the brain of the system. Hence, capable of having a system which does not depend upon any external source and has a sensing capability.
Capacity to have multiple states provide a large variety for scenarios of intercommunication between states. Thus, every unit achieve possibility to different behaviors within a population with the same state or collaboration with the other ones. We started research of state intercommunication with the closed state. Its main advantage are mobility and possibilities of several packing strategies. Based on facial connection, we can achieve different growing patterns depending on direction of growth. We started researching linear growth to investigate potential configuration that can be achieved by this state. And since unit has a possibility to transform, we start implementing this transformation in order to figure out how it can influence geometrical flexibility of the structure. And this explorations gives us a base for communication models later on. So here you can see how implementation of different rule sets for growth can bring us different kind of geometries. Also, we started research curve solver as an opportunity to achieve different types of connectivity and to create some three-dimensional structures. We started to just making some lines, and you can see here we have a rule set to have some particular number of units that are packing differently and guiding by these lines. However, just growth cannot provide wholesome geometry, and at this point we start developing our we start developing an open state that is crucial since it has a capacity to become an infrastructure for other states and can provide more efficient passes for other units to migrate from one place into another. Another packing strategy that can be achieved by implementation of flat states. The main advantage is interlocking between units that can help to create two-dimensional surfaces. And since this state has a certain capacity to mobility and certain transformational range, it can provide some mobility. And this is useful for different kind of scenarios. Here you can see for climbing ones, you can climb both surface by attaching with different sides. Also, by this state we can achieve the two-dimensional growth by implementation of interlocked passive units and active flat units.
We started to take these rule sets and started to build a system that can solve different kind of connections that can achieve a goal. Here is a negotiation system where these individual units try to pass from one state to other in order to solve their path and in order to negotiate and reform a structure. These kind of adaptive solving strategies can help us solve a complex problem which has a single goal with multiple units. So at right, you are seeing a large amount of human units solving the same problem as the other ones. As the adaptive reconfiguration also helps us change the goals and make these units readapt and renegotiate their formations. So here we are seeing these units changing the complete structure based in sequences based on their connectivity in cycles. So to combine these three different states, we started to create a simulation that builds a three-dimensional communication strategy. And we took individual elements and research that we made before. We started with the communication strategies and build a building system. Then we built a growing large-scale negotiation solver and a network system, which defines the main rule sets of the context. And we started building the basic relations of these units and how they are going to negotiate and form vertical and horizontal structures. Here you are seeing them combining to each other in order to create a column, and they are connecting with the flat packing strategies, and they are bridging with the open strategies. Our communication model in a three-dimensional scale is based on units talking to each other. And they ask each other what to do next, and they communicate inside the clusters in order to find out what they need to do, where they need to go next. So the whole cluster negotiates the next position of the unit that should go. Here you are seeing individual types, so type 1, type 2, and type 3, that has their actuation patterns implemented in their knowledge. When we start to combine these knowledges, we start to see emerging structures, and we start to see different communication clusters, which enables these units to transform themselves from one point to another. We took our adaptive reconfiguration principles and implemented into the system so that these growth strategies can renegotiate their configuration and create porous and unporous structures in different densities. And as our the growth strategy is based on communication and based on deployment of these agents, their start position and their construction planes are playing a crucial role for us. So we started cataloging them in order to see what kind of spaces we can achieve with them. So by combining these elements, we are proposing an adaptive communication system for multi-state modular robotics. Thank you.
These are the earlier deformation. So these are earlier deformation model studies of actuation patterns, and we have some stick models which helps us to understand how the elasticity and the actuation works in that. This is a example model that we created. These are different states of aggregation and self-structuring. Like this is a flat state, this is an open state aggregation, this is a flat, this is an open state again. And here we are trying to create a hybrid model between the closed and an open state, how the spaces from the column is transferred to the surface and how they are negated based on that. On the prototypical point of view, we have two prototypes which were used to study the actuation patterns created in those videos. And then we created a self-stable system which does not require any output source of pressure or power. So this is a stable system on its own. And we finish with our stick models that show certain states of self-structuring as well. Thank you.
Would you mind going back through the explanation about the single unit, how it builds itself? So it climbs so you have one unit and the second one climbs it and continues to climb. Could you go back to that? Yeah, those set of images. You described the idea of shifting the center of gravity so that you set the thing to rock over, which I understand completely. But I'd just like to understand a little more clearly how that means you can climb, one can climb the other unit. It's using magnets, I presume.
Using electromagnets, which have a capacity of...
Would you mind if you could just show that? I just wanted to understand a little better.
You want this one?
Yeah, this one.
This one is the rolling mechanism. So what happens here is, as this is a complete system, the transformation happens when these two flat plates are in one place and the other one picks it up.
Yeah.
So when the three segments are on this side, and when you pick the other one up, it shifts its balance to the other side. So that's how the rotation is covered.
And so when you take one and you take a second one and it attaches to it, it's talking to the other one, so it's shifting its center of gravity to allow the other one to move up it. Is that correct?
In the case where there are multiple bots, but in this case, I'm just shifting the center of gravity on the segments level, and then picking up the other one.
Could you go to the multiple, please?
Here what is happening is, that plate becomes like these.
So that plate's now attached to the other through an electromagnet.
That's like an electromagnetic system that is.
And it's hydraulically drawing itself up?
Yeah, there's a piston here.
Yeah.
Which pulls itself up.
Yeah.
In this way. So there are pistons on the side and there's a
Yeah. But there's always a particular geometry they have relative to one another when they meet. They have to meet in a particular way to do that, so that each face meets a face.
Each face has to meet a face, or they have to open and then connect to a surface and then close again.
Yeah. So when you go on to the multiples, you said that they can, I mean, these models appear to suggest they can link in a completely different series of relationships. Is that correct? Have you done that? Have you actually been able to do that physically? I mean, you've shown it as a computer model, but not as a physical object, right?
Physically, we were not able to, but I ran out of time to analyze
that. No, I mean, it's a very impressive piece of work, actually. I think it's a remarkable achievement. And you know, the fact that it's self-building is I can see I understand in the time you've not been able to do it, but I think what I'm interested in is each of the objects you've chosen. You've chosen a series of 3 pieces, 3 modules, and I guess there are a whole series of different modules you could go on if it evolves, allowing you to create even more forms. So I think very impressive.
The 3 modules are 3 states of the same.
Yeah.
And I think that's, at least for me, that's where I think the real intelligence is. Because otherwise it falls into a kind of component project. But before, with this transformation, I mean, all I was trying to say is the 3 states are part of the same module. And I think that's I think where the exciting aspect, at least from my perspective, is that they seem to mitigate, I think, a lot of the kind of component-to-component problems by introducing how face-to-face connections actually start to happen.
Thank you. So, in your presentation, I've heard a sort of lack of technical terminology, and sort of normally under normal circumstances it's very commendable if you're explaining very sophisticated concepts with on layman's terms, but here it's almost the inverse, where, and you've done so remarkably well, but you show a grasp of concepts of spatial amorphous computing, a grasp of concept of, you know, how do you compile a global state to local actions, which are incredibly novel domains of computing, but you're not using the terminology, while you've obviously are demonstrating a command of it. So a bit more terminology would be okay, because you kind of underscore also that you've understood that on a scientific notion. I thought that the beginning of your presentation, where you were using actual AND agents, was remarkable. And the thing is that what I don't understand, the thing is that in your project, the scope of the project is remarkable, but why have you chosen to develop these physical robots rather than sort of, for instance, building you see the very final panel, why not sort of build a larger aggregation of these elements? And my thinking is that the project would have been perhaps better if it would have been more focused in terms of its architectural outcome, which I think is the potential for that is more visible in the last panel, or that resonates stronger with me. Because let's say all the mechanics in the robots I find inelegant. It's my preference, but all these tubes and actuators, and while you show such a lot of beautiful work, right? So in terms of an aesthetic choice, I find that a poor one. While I also have to underscore, let's say, the accomplishment. It's also very, very clear. Yeah.
Thank you. Well, I'm not sure if we can judge the aesthetics as an independent criteria altogether. I mean, these things are, for me, incredibly beautiful through their performance and through their intelligence of the 3 states and the behaviors, I think, and the computational power you and development is adding to this, because they become animate creatures we can relate to and marvel about their transformability, aggregation. And I love particularly the way you zoom in on, for instance, the genetic algorithm of optimizing movement relative to actuation amounts, and then you seem to have the similar process and project where aggregations now move towards a goal, and that's, as an next step, quite wonderful. And I do find these structures, because I'm now projecting onto it, that continuous rolling over and evolvement, and also the beauty of the detail, the way these things, I love these interim states where you actually see, I don't think that's the most in the final computation, but the intricacy of synchronity, where something has to open, something has to flatten, and so locks into the other and roll over. Would have to be interested to quantify how many simultaneously interactive, first of all, elements, and then each of them has their own, of course, series of subcomponents we need to synchronize. And that's why I commend this, because this is proof of concept, both with kind of starting to see the technical issues of the physical transformation, but also to run this, to interface out of the computer into the real world and have a robotic piece which actually behaves in ways which I find stunning. So that's, and to foist and kind of another aesthetic at that point is not interesting, because we're just proving of concept here. And I think there is of course, in the final analysis, there would be other elements of optimization, lightness. How would that mean to be out without all the cables and so on? But it's beautiful in terms of its behavioral complexity, and that's the agenda. And I sense it in these models.
I'm gonna have to say though that I like the mechanical quality of this project. It's almost Shintoistic. There is this idea that something inanimate become animate. I even like them alone more than there. Somehow this brings it back to an architectural problem, and although the intelligence of the system, I could imagine this being static and being only 3 modules, and you still get this. These ones, I think, bring this into a completely different realm of pet. This is actually something that has an incredibly correlation, human correlation. They act, they move, and they are threatening and domestic at the same time. They don't speak the language of architecture in any possible way, whereas this do. And this one somehow create a weird characters, weird relationship with the philosophy of making that is completely foreign to architecture, not the idea of an animate object that then can construct something else. I think also the singularity is interesting. I'm imagining if I would have 1,000 of this, if they would still be pets, or they would be threatening almost in their behavior. Here, somewhat, the scale is so different than, I can imagine this entering a different realm of architectural problems. This one are a game changer somehow of what we imagine architectural components to be and how they respond to us. The clumsiness, I think, is, I understand why to you they're not, but they have a raw quality to them that I think makes them even more human in a weird way.
I'm very impressed, guys. I'll just leave it at that. I think you've done an amazing job. I love the way you've presented it thoroughly, from the very beginning concepts all the way to the end execution, and you can see how you've steered it in a direction where you could just continue to follow this path and evolve this very concept and take it a while, which is very well done.
For me, I agree with Adam. You've obviously come up with a really great solution for how to reconfigure, modules and how to transform a structure. But for me, a bit, I think, is lost in terms of why in the presentation, in terms of, what are the goals for actually reconfiguring a structure, a building. I think the project is great and it's solved a lot of problems, but for me, still the question of why is out there.
You've got now a couple of weeks, I think, to take a terrific set of results in the project and turn them into a kind of research document that tries to re-express the driving question or questions that have taken the project to where it is now. And I think it's enough time that you can fold into it a speculation on how big this stuff is and why. Like, I'm curious how we would ever introduce the topic of scale to the project. And there's a difference between scale and size, we know, right? I mean, they have physical dimension, and it seems like the physical dimensions of each kind of model-making exercise have been driven by, for example, the pneumatic components in this case, or the size of the tubing available, or how small can I reasonably laser cut material and get little holes next to a surface. And you can explain why the models are of the form they are, but what's harder to explain is how we can look at these kind of images and imagine scale in its application. And to me, it's such a kind of masonry architecture. It's it's bricks, but like really weird bricks. I mean, bricks that can do more than what we're used to, bricks that can build themselves into the structure. And I think, if you take the brick and the way they're used to make these buildings a quarter millennium ago, the bricks had a dimension that related directly to that physical material and the fact that somebody with a hand was going to stack it and another one was going to come along and get stacked. I think for you, what's really exciting is that I can, if I want, read that thing as a 1 to 150 model, and then they become sort of big superstructure, room-sized superstructure, or I could imagine it as a 100 to 1 model where you're actually operating at an almost molecular scale where questions of energy and force are much easier to imagine almost immediately and allowing these things to lock together. The electromagnetic energy that you're saying is in it now could as easily occur through static electricity if the mass is light enough that static electricity could hold it together. And I think you ought to use the next couple of weeks to just throw it out as a series of questions that you can, before someone takes this and tries to either turn it into a superstructure or a mechanical model or a piece of nanotechnology, that you can really lay out that framework. But I think that is one of the demands on this idea of a tectonic-driven form of research, which this is. It's a different kind of tectonics, clearly, because you're literally putting energy into the inert material, but it still has the same set of questions around it. And I don't think you should shy away from them. You've basically tried to let the model-making demands answer that question for you every time, and I guess with the hope that critics would come along and say, well, what if we imagine it as a skyscraper, or what if we picture that as a 1 to 50 model of something? But I think in a way, you're the experts of it right now. You know the system so well that it'd be really interesting to see what your take on it would be. And we got a couple of weeks to do that, right? One final point, which is that because you're using one of the oldest imaginable architectural conceits, which is Euclidean geometry, so for 2,000 years, a discipline driven by a kind of idealized geometric figure, which you're using, I find, interestingly, in a way very different than a geometric architecture of classicism or a space frame in the 20th century. You're creating a kind of a supple, loose structure that can fold on itself. That one of its other features, though, that could really advance that idea of the geometry is that you can now operate in a system that would have millions of components rather than a couple of dozen or a few hundred, the sort of scale of numbers that's quite familiar in architecture. I think what you would get is then the possibility of sort of wave-like behaviors happening much like a cellular automata, where it's precisely because we've got such a huge number of elements involved that the question of timing and how we move from one unit to another, iterating over hundreds of thousands, would create almost snake-like or wave-like transformation rather than simple one-to-one shifts of two neighbors. And I think that's an amazing potential in it. But it would almost require that you model it deliberately with an expectation, much like a brick architecture, that it only becomes a structure when we deploy huge numbers of things. Which again, I would only reinforce, I think, the potential for a different kind of form and not just structure in the thing.
I mean, I think a lot of those points are spot on. I think the issue of population and the relational aspect of how these things negotiate is part of how you guys have worked on it up till now. But I think this aspect of what Brett is talking about, a scale, is actually an affordance at the moment to see how population actually starts to influence it, not so much in its own integrity of what it's creating, but in terms of now you have a model that has potential multiple applications, and to be able to guide that judgment. So for example, this isn't an architecture that's fixed or finite or has a blueprint. This is dynamic and evolving and time-based, and the drivers for that would be very much tied to a certain context awareness and a context response. If that is as a miniaturizing version of that scale, or if that is actually for a mega structure version of that scale, the implication of the demands of how you would ask the question would be different. But I think it would be interesting because I think you do have a framework in which you could ask those questions through your project, its relational ability, its population. And I think you could actually generate a possibility for very different kinds of ideas of what architectural communication strategies, integration strategies could be. And I think that that's part of the things that I think are quite valuable of what you've done. I mean, to talk about the projects from an aesthetic perspective, I don't think is the most important thing. I think Patrick's point of proof of concept is absolutely important, because these aren't prototypes that are going to go out and just build the world yet, but they're building a certain understanding that allows them then to go and to drive the computational frameworks with population as actually something that is at the heart of where the variability would lie. So if those guys are 1-to-1, like Brett was mentioning, or 50-to-1 or 1-to-50, that would have amazingly different kind of burdens on what this thing would be materially, what would be actuating it. But fundamentally, as a way, as a thought experiment, I thought, I mean, what Brett is mentioning is interesting, because that reflection then opens up, let's say, the future trajectories of what you could do. You know, and I think that that's something that in the book, you should probably hold yourself accountable to try to figure out what those things would be. And still allow that actually to nurture maybe how you decide you're going to spend your time after this place.
Yeah. I mean, I think the other thing which needs to be coming in and is not too difficult to bring in is, why is this a good idea today to have these kind of structures? And I think this is where types of event which we now look at all over the world, requiring this in terms of an event scenario dynamic where we want to go to an event and experience multiple situations in a rapid sequence. Let's say you come together, 500 people, you know, it's not only about 500 people listening to one thing and then going home. It's 500 people doing all sorts of things and mixing and matching in groups of multiple sizes, and this continuous reconfiguration of these diagrams and interaction diagrams, something you would have in a conference scenario, a kind of expo scenario, many scenarios, and that's where I would like to see that to be played out and could be tied up with. I mean, you haven't done it this time, but I hope the next iterations of these, with the crowds which animate that and see these envelopes evolving and surrounding them and transforming. That would be the why. The why would become very, very obvious and yeah.
I have to say, I also agree with the fact that we have here a good delivered proof of concept. I think it's a mistake to think of it as purely geometric project too, because it's clearly a behavioral project and there's a lot of in-between states and variability there. For one thing from my side though is I think between now and the end of the book, it's really important to speculate a little bit and illustrate for us the goals and potential of the research. Because at the moment you're kind of safely positioned in delivering, like you've proven that you can do the actual physical mechanics. You've also proven that you have a simulation that works. I think this is fantastic. But I think you need to demonstrate a little bit about how this would operate. And that doesn't necessarily mean a scenario like Patrick's suggesting of event or something. I think it's more about, like you had goals, for instance, right? That the bottom-up rules were following. It'd be nice for you to clarify a few goals, like you had one about columns and things, but it'd be nice to clarify whether there is a fixed state that they want to arrive at, and even when there's other perturbances and things, they have to maintain that state. That could be one thing they do. Another thing is they might have to go from one fixed desired state to another one under a certain condition. And these states somehow have to bring it back into the architectural realm. So, and I think you're already demonstrating you can do it. I think it's more about clarifying that something like this can be about kind of dynamic stability or near equilibrium. Like you can be bringing back something to stable and trying to maintain it as stable, or you can be constantly allowing it to change while maintaining a certain order. But I think it has to be communicated through these dynamics of order at an architectural level, rather than just leaving it as, hey, we have developed the system and that's that, right? And you're more than capable of doing that.
Yeah, from my side, I also like this project very much. I think the progress from the conceptual idea to the prototype is really promising. I always think with this modular setup, the whole structure is as strong as the weakest part, actually. So the question is how lightweight this structure can be, how much force can it have, and what can you really build with it. So in the simulation, it's fantastic, and you see you can build really a fantastic maybe buildings or structures, but if you come to the real world, then you see how complex it is just to add two pieces together. And the big challenge actually is how much intelligence, how much new technology, how much new materials can you bring in such a robot? How big has it to be to finally be able to bring at least hundreds of these pieces or thousands together? And this is really a big challenge, and there's a lot of work to do.
afternoon. Hi. This is team beside, including all three of us. This is Yu Yan. This is Milk. Nai. This is Yanga. Myself introducing. We'd like to introduce our project, which we were concentrating our research on the energy embedded responsive kinetic structure, in which we are hoping our main aim is to have this structure and the users in the building like interacting each other responsively. Basically, like starting from the research, like where we find some examples of the configuration of the building that is influencing the situation, that is saying like the placement of the building structure is kind of showing how like people would like use the space. And the other way around, like there are some other examples we can also find that the situation influences the configuration of the building. And we are aiming to have these both interactions like occurring together, in an interactive way. We see a lot of examples that's taking a lot, like long time in a large scale, that's transforming, taking like a huge machine-centered transformation, and we're aiming to have it like in a short time arrangement in a smaller scale that can happen more like frequently in a daily kind of transformation with the human in the center of everything. So we've been investigating all this research to figure some elements that we developed and like apply to the building structure. So starting from the research part, we started from the biological research where we could find some examples in the nature, which was having throughout this like pollination, explosive pollination, we can see this movement that's very rapid, utilizing its embedded elasticity in it. And we tried to come up with some, we were analyzing that movement. And we were coming up with like 3 different steps the transformation happens. First, it's deforming to start embedding the elasticity in the structure. Then it can be transformed with a small amount of power. Then in the end, when it stops the transformation, we can also stabilize it by making the density in the structure higher so that it's not gonna move anymore. So these are some ways we figured to control the research we were going on. And then further, we were like starting to have these combined together to come up with all different types of forms, and also by combining them, they act in different ways and in a more effective ways. So these are some examples of the research we've been going through with the model, especially with something that can start having this elastic power that's embedded and to utilize this power in it. Sorry. So based on these prototyping studies, we tried now come to the application to the augmenting the project we're working on.
So to design the building, we tried to figure out the different user group, which is, there are lots of different user groups, but we divided into 6 different groups, which is architects and architects, associates and supporters and clients and visitors. We divided this user group depending on how much they spend time in the building, and then where they stay during their in the building. And then we figure out their number of user groups are different depending on different cases, and we figure out mostly architects are staying in the office, and then visitors tend to stay in more public area, which is gallery or like cafeteria. So depending on that, we could see in different cases, we need different area of space for the building. For example, when there is no events going on for the public, there might be more space for staff people for Jaha office. And when they are like open to public, like temporary exhibition going on or open lecture is going on, there should be more like space for public. So depending on that, we try to utilize our prototype to adjust these differences, a difference of area of the building. So we put the program in sandwich way. So and then we put our transforming part in between area, so we can start to utilizing and changing the area of building. So when you see status A, it is closed. So visitors group and like office people groups are quite separate. But when the transforming elements start to open, they start to mix up. And then when it is completely connected, they are starting to meet in between area and then start to interact each other. So the left one is original building, and we add mezzanine floors, basically added mezzanine floors to make our proposal, and we add one more core for staff people. So starting from staircase, we have a petal room and connection and partition and petal chair and office desk set and canopy and roof opening and facade. Those are our 9 elements, which is our prototypes. And we were gonna show you short video for the interior of the building to note some like atmosphere of the building. And there are 4 scenes from 9 a.m. to 9 p.m. And the view is taken by different users. So this is taken by public user, outside people, and then when they get into the lounge, they meet petal chair and staircase, and this is deactivated mode, so they should use sub connection circulation. And then when they go to the open area gallery, they meet partition, and then they can enjoy the gallery. And now the staircase is activated, so people can start using this staircase, but instead of that, petal chair in the lounge can be deactivated.
Coming close by, then you can start activating, like actuate it itself, then it can create this space for people to sit, and you can also manage to change the shape of the chair yourself, the way you want to sit. And this is kind of starting to signaling this, how to use this space. So like as more people are coming closer to this area, then like you start to have like you start seeing more of the chairs, which is creating this atmosphere of seating area for resting. Then they can get acknowledged by the transformation of the chair that there will be more people coming in. So it can start enlarging the area, and that's basically how we are trying to utilize the chair, and that's the mechanism we are thinking to have. So it's gonna, that's basically transforming and like changing, just simply by changing the angle of it, and as it gets into the position, it can rigidify its form so that people can sit on it without any more of the transformation occurring. Then also another type of chair we are thinking to have to give some more mobility to it so that we can easily move it around in a folded way. And once it's at the position, we can just set it down, have people sitting on it. And this chair area is also kind of influenced by this staircase in the center, which is coiling itself accordingly to the program that's going on upper floors. So like this is basically changing its status to decide if it's open or closed, its connectivity for the people. So it's basically signaling if there is program going on on upper floors or not. So for example, when there's in the gallery area, if the exhibition is in the preparation period, then there shouldn't be any public people enter. So then you can just have it rolled in so that it's not physically not possible to enter. And when it's when the exhibition starts, then it can start be activated. And also, like when it's rolled in, you can see this area down underneath with the chairs, so that we can utilize the space in a more clever way. So that's basically how we are thinking to have this mechanism of the chair. So like as it is rolling in, and or rolling out, it is also gonna like control the status open or closed status of the step itself on it.
So when the petal staircase is closed down, it's not actuated, but when it is open, more visitors can climb up, enjoying the gallery. So as I previously described, in case 2, when temporary exhibition going, visitors are more than like case 1, so we can see there are more space occupied by visitors.
And there are some extra connections that can be used for connecting these floors when the exhibition is not on. That it's basically inspired by this simple geometry that you can like fold and create this potato chip kind of shape, and that's gonna start creating this connection between 2 floors, and also have this open ceiling, so it has like more lights coming in. That's the mechanism you're thinking of, and it's gonna allow some more circulations. And there are some partitions that's coming, basically just coming from down from the ceiling easily, and it can like start creating these rooms, and it can like start dividing the spaces for having like all different rooms for the different types of exhibitions. So you can easily change the circulation of people, or you can easily create a room for a specific type of exhibition you want to have. And it's simply activated by having this constraining fabric with the shape wire introduced into it. Then it's gonna start creating this kind of shape coming down from the ceiling.
So depending on how the partition is positioned, people are start to move in different ways. So the crowd makes a different path from each other. And this is cafeteria in the noontime, and then you can meet lots of different user groups, and you can climb on the petal room for the lunch conference, and you can meet lots of mixing people. And then even petal room can be connected to each other, so people can be there. And then when the meeting is ongoing, the petal is closed down for enclosed area. So these are previous studies for the petal room. So we started from the single petals, and we tried to combine, and we finally figure out individually controllable petal room. So when it is deactivated, people can use below area even larger. But when the meeting area is needed, the petal can be open, and then it signals people to climb up. And then these are filled of the petal room, and then these can make a bigger conference room. We are imagining this petal room can be controlled by a railing system, which is attached to the column. And then also we are thinking to have surface segmented so that it can be used as a table or chairs. And then one good thing about this is it transforms when the petal room is changing, so it transforms all together. So when the petal room is closed, there are not much interaction in between, but when the petal room is open, there are lots of people can communicate in the meeting room area. So that means building can be more interactive itself. This is office area in the afternoon, and then this staircase is only for staff, and then it helps to light comes in better way. And then when you go to the office area, there is office desk set, and then it can change its position to adjust their according to their project, so they can make different position. And when it becomes meeting mode, the partition comes down, so it makes internal meeting area.
So that is about the staircase on the right-hand side. You see, that's specifically just used for the circulation in the private area. So in this case, it's not really coiling in or out because it's always supposed to be connected throughout the whole stories. But then it is rather about these petals attached to it be activated when the people come close. So it's gonna like start making these steps, or when there's nobody climbing up, then it's gonna fold down in itself. So it's gonna allow more sunlight coming in to the interior area. And in the office, we have these desk sets that we can utilize for in all different types of spaces, especially because of this architecture office where they have a lot of different projects going on, and at different stages of the projects, they need a different number of people. So the team always really changing really frequently. So we want to have some furniture that would adjust itself easily for that. And so we can have all individual seats, or we can even have them all transformed to have a larger team kind of setting. And also when the partitions come down, it can have this private meeting room. So that is basically how we are imagining the partition is going to be really easily transformed by just hand, because it doesn't need any, it needs to be very frequently changing. So it doesn't have any mechanical stuff in it, but it's rather just done by, manually by people who just needs to change it.
And in the nighttime, office people can have cluster party in the rooftop, and then people climb up to the rooftop by petal room, and then they see canopy, which is for people to rest.
So now as it gets to the exterior area of the building, we are more thinking about this environmental factors that can affect these transformations. And as we are going through this sunlight to the building and the depth of it at different time of the day, we start seeing this area, it's always heated, and always, sometimes some of them are kind of hidden. And we are starting to come up with this material that can react to sunlight, that can start transforming it by, especially in this case, we were getting into shape memory alloy that can change its form as it's heated up. So as we are having two different layers, one that is changing and one that is not changing, then we can start having this deformation of the entire structure. And we are starting to come up with this idea of during the daytime when there is sun, then we can start having this petal part open up. And as it cools down, we can have it just back to flat status again. So during the daytime, we can have more sunlight coming in. And when it's not with the sun outside, it's gonna just close down for a closed, enclosed interior area. The canopies are working in a similar way, but then it's a bit smaller, and we have another feature that would rather follow, react to the position of the person that's around. So it's gonna make sure it keeps keeps the shade on the person. But then if you don't want it, then you can now manually transform it, in which way you will get some more sunlight. So it depends really on how personally you like the status of it. Then you can start creating also this kind of pathway as people go through it.
So depending on the canopy status, people can gather, or they can spread.
And the facade is another part that's reacting at the largest area to the environmental factors.
And the idea of the facade is we're trying to apply both environmental parameter and observer parameter by using this rotating mechanism, and also the configuration we generate by following this the outline of the slabs and also the balcony. So we have this geometry of the strips, and we further categorize different three different colors referring to different functions. For instance, like the blue one is for office and the pink one is for library and gallery, where is the public area. So they can have different configuration by controlling the curvature, because as the experiment we have done is when we make the curvature thinner, we can have the weaker point, which make we can control the rotation. Yes. And also, this rotating is following the sunlight. So from the early morning to afternoon until evening, the facade will have different configurations. And this is the mechanism describing how the rotation applied to the strips attaching to slabs. And so
overall.
This is the overall configuration change of whole day, depending on the sunlight. And we expect our building can react to different situations for both user and environment, which can be adaptive building by using our transformation prototypes.
Thank you.
To briefly introduce our prototype models here. So these are like the one-to-one model we were trying to fabricate for the chair model. That's so it's basically this area you can just sit on. Like this is already like rigidified, so this is the status with it's not gonna transform anymore. So when you have like the weight on it, it's not gonna change. Whereas on this case, like for example, like when it's not rigidified yet, you can see it transforming to the other position as well. So like you can just decide the way you want to sit on, kind of things. And this is the mobile one. This is like fixed on the floor model. And these are some prototype models you can see. Like we were just going through some different ways of connecting this, like different, depending on different way of connecting, we can have some different surface area. And these are some surface, I study some different types of surfaces we were trying to have. And these are the prototype when we get into the actual elements, prototype elements in the building. Like we were coming up with some ideas of the staircase as it's moving. Like this is just basically doing the same thing as we were showing on the screen. Then these are some fabrications of this wire so that we can create some different type of space and also some different, there are some different ways of actuating it, and it can enlarge its space inside and or it closes itself. So the basic idea to utilize as much space as possible. When it's not in use, then we want to use the space outside for something else. And these are some different types of the surface study for the room. Oh, maybe it's okay. And these are the surface, another like surface study. And that's 1-to-100 model of the building where we are trying to like show the positions of the things that we were introducing, which is pretty much what you can see on the board panel. Then so we want to maybe demonstrate. facet model we want to demonstrate, just to show how these strips we are imagining it to move, reacting. Sorry, maybe we're going to have to wait a bit for loading the program. So. Yeah, maybe this can be something we can show in the end of everything, maybe after for a while, yeah.
Sorry for technical problems.
I think this notion of bistable shapes is really interesting. From an efficiency standpoint, I think, and practicality as well. So I love some of the studies that you've done here with that and exploring how to really make the building come alive, how to make it adapt sort of real time to the environment, I think is important looking into the future for really all buildings that we build.
Can you explain the chair that locked off with the rods inside the tube? I didn't quite understand how that worked.
It's at this moment it's kind of theoretical thing. I mean, we are imagining because when we are using this, when we made this model, it was we used PVC pipe. Then it was easily transforming, but then at the moment when we want to sit down on it, it's gonna still transform itself. So we tried to put the rod inside, going through it in this shape. Then it starts transforming itself. So that's where we found if we have this pipe running in the middle, to shape this. If this is rigidified, then it's gonna stop transforming. So we are controlling the density inside. So if the material that, the small material, we are imagining the small materials that's gonna run through the pipe, and when it's not really dense, then it's gonna have some spaces for that, for the pipe to change its status. But then when we have those materials inside, all really close to each other to make this dense cluster, then it's gonna stop, it's gonna rigidify itself and stop transforming. That's the main idea we're having for the rigidification.
There's obviously a whole science on jammables that you might want to look at there. You could do something similar with vacuum and pellets, or with oil, if you were to take oil and lock it off because it's non-compressible. It might be worth looking at, but very interesting. I love the idea of the facade that follows the sun. Very efficient and simple mechanism there.
I think the project is quite accomplished architecturally, which it shows also an incredible dedication to one single solution applied to many different programmatic aspects. I think the facade is one system and the interiority is a second system, and you really went through every possibility that the shape could give you. I think now probably the interesting part would be to decide which one would not work, meaning that there is a faith that this subtle shape could do probably too many things, and I think you understand perfectly the limitations. There could not be stairs, for instance, but there could be incredible umbrellas. There could be chairs, but maybe not great partitions. So they have a range of possibilities. Also the range of possibilities of what happens when you swap. I was imagining, what if it's not all white? What if it's double-sided and you actually have a second coloration, and suddenly it completely changes the mood of the space. As of now, everything is white and perfect, and I like that. But on the other hand, I think, what if the surprise would actually start engaging in architectural lighting, coloration, shadows, and really play on that so that you can get some more mileage. I think the materials itself also, the fabric, the tensile quality, might not lead to all the functions that you would like them to, which is fine. The computer allows you to do it. Then when you go on the physical models, you understand that that's not possible. You've done enough to know which one don't work. And I think it's okay to let them go. Frankly, I don't think that you need to have a complete system that repeats itself in its geometry, especially when a geometry is so specific, in order to prove a point. I think proof of concept is done, I would say that now the best thing you can do is actually decide and edit away what doesn't work and allow different elements to come into play. I think the project is fragile, and I like that. It manages to do something that not often architects manage to do, which is keep some lightness to it, and I think I'm interested in this idea of fabric and materials that somewhat defy the sense of gravity and allow a certain level of lightness, transparency, and playfulness to enter the realm of architecture, which is usually quite difficult to achieve.
I think the project is really strong in its initial and final phases, in a sense, right? You go from this initial stage with the piano wire. It's very beautiful. The fragility and elegance of these models is palpable. And then what I appreciate is sort of the seriousness by how you go about it. Sort of the rigorous analysis about how it affects the operational mode, occupational mode of the building. That's really great. But there's this kind of in-between phase where you are sort of putting forward products that is not sufficiently well developed. Like, for instance, it's still a little bit difficult to foresee how this would work as what kind of fabric you would use to make this work as a staircase. So the other part of your project, which is more developed more accomplished as a product in a sense, the facade, doesn't have this kind of analysis, this kind of seriousness in terms of analytic aspects in how it affects the occupation or the function of the building. So perhaps, let's say, that analytical quality that is in your project, maybe you could extend it also to the facade. I think that would be a welcome contribution. Yeah.
I particularly like this idea of using this snap-through thing, the strain energy, but and there are a whole series of smaller projects within the project. Some more successful than others. The staircase, not so sure about that. I didn't quite. Does it rotate? The stair. Okay. But the one I really like, because the thing about this snap-through thing, strain energy, is you're pulling the thing until it reaches a point where it's got potential energy. That's your understanding. It snaps through the other side. When you get bigger, that energy increases, not linearly, but some exponential thing. It's massive when you get onto big pieces. So it won't be so successful when you start building things big size. But there were one or two things, and this thing here, what do you call that? The room. I thought was fantastic. There's something in that. You know, I saw a surface unfold to create a staircase. It's beautiful. And if it was one thing I would take from that, I'd go away and think about that hard. Because there's something in that. Because you're talking about the fact that you're driving it, actuating it, physically actuating, or mechanically, or whatever you're doing. There's something really beautiful about a surface that suddenly changes, exposes a three-dimensional thing, which is stair treads. And I absolutely love it. I also agree, I like the facade, but I don't know where the facade came. It seems to me there's something there that's also worth pursuing and not being pursued as far yet. But I would carry on pursuing that too. So lots of elements, some more successful, one or two outstanding. I think that, I would like to work on that one.
I think it's a terrific piece in a way for speculating on a quite a large ecology of elements that, particularly in a studio like this one, in fact many parts of this school are treated as secondary parts of our universe. I mean, there is a kind of superstructural bias, you could say, that good old-fashioned modern architects have made sure we all live up to. And what I find interesting in even the big section, or two or three of these views, is that in a way you just take it as a given that there is a superstructure, and then the speculation is really on what's left after that. It's like, what happened 100 years ago when Maison Domino put in place and imprinted on our brains that's the only thing we should work on? You know, in a way, you're hinting at your leaf or petal can be not just a chair or a partition or a stair, but it's, you know, when I look at that model, suddenly a soffit you know, an almost degraded topic today, the idea of a ceiling. Like, who the hell works on ceilings anymore? You know, we'll make the slab and deal with it, you know, we'll hand off to an interior architect, that other kind of problem. And in a way, it seems like you're still opening up what the breadth of that landscape is, and I would just suggest you continue to push it. And the idea that those petals can not just be seen as singular elements, but like in that model, an array of surfaces in which, for example, if I need a chair, all I need to do is sit down in space and a part of the floor is going to pop up and catch me. Like if you built sensors into it, you're done, sort of thing. You know, it's not just that these are elemental pieces, but it's a way to rethink not just the idea of a surface, but really the relationship between the interior as a universe and the superstructure. And I think that's just a really fantastic thing to take on with the confidence that you've done. It seems like, though, you're still taking baby steps about how big that might be. There's one or two hints at a sort of tabletop high surface, but in your world, of course, that's a real project. You know, how many different kinds of tables would this office need? How many different kinds of partitions? It's not just one category, but in your world, it's a bit like Eskimos and snow. There's 30 words for that stuff because there's such an array of different potentials, and it'd be really terrific. Mezzanines, like a topic that no one, like in this school, all year I'll hear the word mezzanine once. You know, it's like this strange, secondary, degraded, modernist idea, but for you, an interstitial floor sitting between the superstructural levels, again, is an area of total discovery. And you should really just map out how big that landscape is, and maybe there are holes still that are, you know, to be filled in.
I like this kind of notion of the kind of Art Nouveau almost. It's like this really cutting edge Art Nouveau and that driving the language. But I felt that perhaps you underserved yourself just the way you frame the project. And I would agree with the comments about really needing to edit down and focus on one element and to look at where do you want this building to be most adaptable. I kind of felt, well, maybe the petal chairs, maybe they don't need to be adaptable. Maybe actually a mechanical solution there would be best, but maybe if you've got this beautiful aesthetic, you can just have them as petal shapes. But I like the notion of the canopies, the facade, but then you need to also look at there's a lot of interesting facade solutions going on in terms of shifting with sunlight, contemporary examples of that sort of thing, and looking at perhaps how your solution will either emulate or go beyond current solutions. So no, I think there's a lot there, but just needs more focus and a more distinct angle.
Just a quick comment, picking up on some of Brett's things. I kind of see the project as a retake on the built environment, like seeing the building as an environment that's constructed in a sense. So, and I think this simulation highlights that it's arguing for something that's totally time-based, which architecture is, but it's very rarely communicated that way. I mean, architectural magazines always take a snapshot, normally devoid of people, with high zoom lenses, and here we have something that's actually a bit closer to what you see in a BBC documentary, but is actually more in tune with the way we actually use buildings and experience them. So I admire that part of the project. I think that there's a sense of how this building is changing over time, and that it's kind of playing a role alongside the activities of people. And I think that's an interesting thing.
I also like very much that you stick to this simple principle with this B-stable movement kinematic. And in the very beginning, when you started the chair, I thought, I don't know if this works. But then you showed the umbrella, and you showed the walls coming from the ceiling, and then you showed the stairs. And in total, it was more and more surprising for me that with just such one simple, universal element, actually you are able to achieve such a big effect. And I think this is very helpful and makes it really realistic if you are able to achieve a big effect with just a very simple principle. Also, this B-stable principle has the big advantage that in each situation you don't need any energy to make it stable or to hold it. Just in the transformation you need a very short impulse, actually. And I think one of the most interesting ideas for me was also the stairs element, because in this case you switched from elastic, more or less textile material to something that is more foldable. And I think this makes it even more realistic to build it and to make it real. So hopefully I get it in my hands afterwards and can play with it. This is really interesting, and like Neil, I would like to walk on these stairs.
Back the question, because am I right that you call that a theoretical model, and is that because you can't sit in it? Because we're dying to see you sit down in the please do. Can somebody, do we have a video of that success or failure? I mean, only because I think to start to argue the project as furniture is one of its great strengths, and the idea still that an architectural project can unfold, let's say like the 1920s with Mies or like the 1950s with the Eames, that an architectural space can emerge out of it, genuine material ingenuity at the scale of furniture, would be a really strong argument to make. And I think the fact that you can't sit in the chair is a fairly damning critique compared to what any of us could say today about it. If you think of the way the Eames talked about their Kazam machine in Los Angeles, you know, the whole point was to actually make this stuff work in some way. It might not be right, but there'll be lessons in the failure that actually fine-tune how it is we can critique the idea itself. And
So the animation is like a good final conclusion of your project. It's really beautiful and poetic, but the facade is obviously static. So if you have 2 more weeks of work, if you can sort of extend that animation to include, you know, the movement in the facade, it would be even better. Yeah. Or it seems it is fairly static, isn't it? Yeah. Okay. Yeah.
I think I think that's a beautiful culminating animation, but I agree what is missing is the crowds and also the shift of perspective, because I think what is beautiful here is, first of all, the various more ephemeral substances, space making, the way they're orchestrated, play with the and their various transformations, and then in their orchestration are figuring and refiguring. There's an economy also there, because the actuation is very, very simple and minimal, and then this is amplified, but when the phenomenal effect of that physical transformation is another story of amplification. And we talked a number of times about the signaling of this, and that's an important element of amplifying the presence of a body, which is then kind of enveloped, and that signals out it's present, and you have these chain reactions of maybe drawing people together. So it becomes a phenomenological project and a semiological project, and using, with a high degree of economy, the kinetic transformation, and with a high degree of robustness. And I think there's also a lot of fixed elements, but which are reconfigured through the elements which move and transform. You also show that. But then there's also, as you said, that element of signaling, of having these waves of activity running through. And for me, it comes together in some of these animations. And I think if the camera moves, the facade moves, and people pulse through within that, and it's all. So these are agent-based models in terms of the crowds and also all the elements. They're all brought under one set of principles of orchestrating and associative logics. That will be the next stage, but I think you bring it very, very close to me. It was very rewarding for me to see that come together. I mean, a lot of them are very dense images. There's a lot going on with many, many elements, and yet there is a sense of harmony and feeling at home rather than a menacing kind of chaos. And so there's enormous beauty in this for me. So thanks for that.
So one thing that this project does that other projects didn't do is to think about the module in terms of surface, which was not a small problem in the other projects, that they always looked at infrastructure because they never had a way to close. And I think this one somehow is quite simple, but the fact that already had embedded an enclosure and made it an object that is immediately architectural and is very familiar somehow, tensile structures and all the things that they do in terms of enclosure, the familiarity of the domesticity almost of the object, it's part of the success of the project. And I think one thing that we didn't talk about is how it moves. The fact that it's a fast movement and somehow something that you could imagine moving yourself. That as well has somehow part of the success, because it's like this little thing that we imagine moving like an umbrella, and somewhat it's the easy quality and the lightness of the project seems like it's feasible right away.
I was just going to say that sort of the surface nature of the array that you don't really see anywhere in the project other than in a couple of these models, I think is really beautiful. And you tried really hard within the entire presentation and concept to sort of work within that sort of method of actuation. For me, though, when you get to the facade, although it's beautiful and it works really well as a standalone piece, I personally would like to have seen that typology be sort of deployed in potentially the facade solution, so that there was a bit more of a tie. And you tried, as I said, really hard to take that concept throughout the rest of the project and embed it in every element, but it's sort of missing from the facade for me.
Can I close it?
Thank you.
Good job.
Thank you. Great. Huh? Oh, this is Milks.
All the best.
Let's put it here.
Why not put on the
No, for now. I mean, maybe we can put it there, but if the camera see it, the camera will get the camera from the internet.
Why?
It's always like here.
No, just put it here.
And when we present, I just move it out and talk about the models.
I think we can during the presentation. Trust me.
I don't know. I mean, I like to that, but the angle is too.
Yeah, for me.
We're waiting for this. Actually, right now it's on Baseball Square.
Yeah, it's outside. It's outside.
Yeah,
right outside.
We have some pictures. Yeah, right now. It's kind of too big. No, it's too big.
No, it's not messy. I think it's good, but it's too big.
That's awesome.
Yeah.
Oh, just this.
Just unplug for a second. And is someone watching it outside?
Yes.
This is on, by the way. But you just don't want to leave it out there unattended, right? Great.
And some people just come through it by the curiosity.
Great.
Yeah. Especially children.
With that one, try and get someone to take a photograph further away as well. Or do you have?
I mean, up here.
Yeah, like this, but further away.
Yeah, for sure.
I don't think you need that one. It's too. It makes it look too small. Scale.
Okay.
You can if you want, though. She's pretty cute.
Yeah. Yeah, that's what we are like.
Just explain this is like 1-to-1 to not 1-to-1 style.
Yeah.
I'll put it here first.
不要再拿回来，不要再拿回来，先拿回去再说。
Let them have fun.
还没有，我没有说，因为我刚刚太大了。你要搬，要搬吗？要搬现在就要搬。
也那个让这个在外面看挺好的，我觉得不要搬下来。搬下来怎么放？
对，怎么放？
然后搬下来就要想好。
Cheap one.
We should mark the price. That was cheap.
No, there's some lecture after. It's okay. They're gonna talk long or short.
Hi everyone, we are Aerofrust. We are in the Ralph Smith studio. This is Chao Kai-rui, Zhang Qiao, Liu Yuan, and Petrolas. We are aiming to create a possibility of the airborne architectures. Aerofrust explains an airborne temporary architecture that is able to dynamically reconfigure in relation to the live social events. Aerial robot unmanned air vehicles, UAV, are utilized to wrap and weave the high-weight three-dimensional thread structures around an airborne scaffold of helium balloons that are able to constantly reposition in relation to a dynamic and adaptive system by weaving activities. In terms of the thesis design, the capacity of the three-dimensional flight assets of the air robots plays a crucial role of the project. And in fact, they have been utilized in many fields working for people such as delivery and exploitation. However, for the airborne architecture we are looking for, this behavior is no longer a truth that the more heavier material or construction is, the bigger UAV is required. So we started to look at a conventional way of 3D print. It is mainly heavy concrete oriented and requires a large framework. Aerofrust instead has adapted to the technology of ferrous thrust machines to fabricate a high-strain, lightweight fiber material optimized for aero construction that operates similar to the spider sink. Moreover, we are looking for another possibility of aero scaffold with lightweight material and dedicated multicopters. The Intercity is a great conceptual idea of airborne architecture. By hanging floating construction lifted up by numbers of balloons to create a mobile, temporary, and dynamic shelter covering the human activities underneath. Then, the common architectural issue of the temporary events is the fact people usually require temporary space or shelter during the time that has its own lifespans. And in some large events, the events such as concert, festival, and annual carnival, multiple activities happen all the time while people crowding around. But we regard the behavior of people gathering, grouping, and multiple activities during multiple scale of events in cities, suburbs, and even huge fields as an opportunity to create airborne architectures. By exploring the different modes of UAV flight control that engage with autonomous decision-making, Aerofrust proposed a practical and created spatial width under numerous on-site scenarios. To begin with, sugar thrust is the first discovery of phase-changing material that creates great volume from small to large proportion. Then, we also test on the possibility of durable material on ferrous thrust machine to create the same property of sugar thrust. Fiberglass, soft plastic, and hot mill adhesives are similarly able to generate a fluffy thrust. In bespoke material, the process of how to make the fluffy thrust is from salt, melt, spinning, cooled, then becoming a thread when it attached to the normal air temperature spinning out by the central force. To approve the generating value of the material, 5 grams of material are able to generate up to 37 long meters of the thrust material, and one single loop of the 50 centimeter can stand for 40 gram weight, and then the 4 loops of the material can stand up to 420 gram weight. This is the first moment of autonomously flying multi-copter thrust collections. To approve the in order to create aerial threat, we tend to generate aerial thrust fabrication on board on a UAV directly. By developed bespoke hardware device, the milled material is able to be fabricated and disproved from the airborne UAV. In a thrust spinner multicopter, we concentrate on the right proportion of nozzle and the speed of the motor to get it right to spin out of the UAV. To improve the custom thrust hardware, we achieve it right from changing the spinner nozzle above the UAV to the below, and fix the angle of the basement support and the attached surface to the ground in order to tackle smoothly. For the real-time practice, the Arduino board and motor controller wirelessly connected to the computer and generate flat thrust thread autonomously. Thus, we are able to print aerially as this simulation demonstrated. This enabled to deposit the material aerially. However, the material will not stay in long in the air. So then we research on the traditional way of the scaffold is limitation against the proposal of air thrust. Instead, we are presenting a dynamic and movable to scaffolding with the balloons, followed by helium to hang the string with the deposit material. And each of the balloons can be scalable, and the one we tested previously is 9-inch only, and the model outside here is the 28 feet. But you can see the 28 feet is 2 feet, and the 5 feet of the balloons can hang. The payload of it is stand to 2 kilograms, and 25 feet can stay 220.
We are going to use 36-inch balloons and helicopter for real project construction, and 9-inch balloons and parrot for laboratory tests. For the helicopter, we developed a bespoke loss package to communicate with the onboard computer to achieve particular behaviors. We can see that in the top 2 videos, we are using GPS to control the UAV to fly through the waypoints, and in the bottom right one, we achieved to create local waypoints so that we can use both global systems and local systems to locate the UAV. This is important because the position information is the basis for our continuous study of behavior. And the bottom left one, we connect the camera to the UAV, which enables us to create behaviors based on the computer vision. We had to develop a custom software to control the UAV in flight and allow the UAV to dynamically switch between these. For vacuum motion tracking, we developed and improved our algorithm to make the UAV fly more smoothly. Waypoint test is the basic test. We achieved to get the current position and set expected position for the UAV here. Once we can get this information, we can start to design behaviors for the UAV. We use Parrot shield here to simulate another UAV. When the mock-up UAV is in the detection area of the real one, it will respond to the target, avoid or follow. What? Sorry. Uh-oh. Sorry. No. It's freeze. Sorry. Just get one computer. It's not HDMI, it's computer. It's freeze. Okay. Another one. Sorry. Sorry.
Why?
但是我不确定这个 video 能不能放出。Can we use yours? Try yours. Sorry.
resolution 有问题吗？
不是，静音。
我没有团队没有静音，它音响连到那了。
OK。
So we achieve position locking and follow markers by developing the SLAM system. So the UAV can use its cameras to respond to the patterns, and we start to develop our local vision-based autonomous behavior. Color tracking was achieved using OpenCV. This enabled us to recognize balloons and move towards them. In terms of behavior, we developed custom UAV behaviors in response to a number of different camera vision stimuli. We achieved to use different tags to send commands to UAV and collaborative behavior between different UAVs. In this one, UAV follows local commands to get rid of the red balloon in the vision and draw a circle as a result. Also, avoid collisions such as in this autonomous flight, where the UAV was instructed to go to the other corner of the room, but must avoid the red threads autonomously to get there.
And based on our research, we started to find a behavior between balloons and the drones. And one interesting behavior we're looking for is that when the drone flew by, it will generate the area that is called gravitation. So two of the objects will have a relationship altogether. And that is what we are going to use we treat the drone, the multicopter is no longer a generator. It can participate in the cities. This is one simple video that shows it can reposition the balloons from somewhere to another place and create a single knot in the air.
We developed a number of different wrapping behaviors that could work with one of a number of positioning systems, but also be able to utilize combination of these. We developed a trajectory system so that when the UAV flies close to the balloons, it will create a list of waypoints to achieve the wrapping behavior autonomously. So we only need to run one code and the UAV can finish the wrapping behavior from all the positions. We also achieved wrapping behavior based on the OpenCV. We find it is more efficient when approaching the target, but it has possibility to miss the stick, which we can improve. So we integrate these two positioning systems. The UAV approaches the balloon by camera vision tracking, and finish the wrapping behavior by beacon locating system. Here is the summary of our flying part. We used multiple positioning systems and multiple UAVs to achieve what we did in the simulation, which is crucial in our project.
These are three types of agents we developed in the simulation. The first is float spinner. It has different range of local version, and it can deposit material and control the material density. It can track the balloon string to rapid. The red dot is the party UAV detected. By different local rule set, UAVs can create different nets between balloon strings. We compared the wrapping sequence. Bottom up is better than top down, because the left one is more average tension. So we use small range of its vision to wrapping small towers, and when their vision increased, they can jump to another tower to create connections between towers. This is the balloon repositioner. It can pull the balloon to its own side. With a lot of UAVs swarming, they can reposition balloons. With this behavior, they can gather in balloons between towers so that the float spinner can jump between towers without increasing their range of vision. This is the rover. It can reposition the anchor of balloon, release the balloon, or extend the string of balloons. With the moving anchors of balloons, the scaffolding becomes more dynamic compared to the repositioned balloons. When the rover cutting and extending the strings of balloons, the float spinner wrapping the strings in their own local vision, they can create different huge floating towers. Then we try to use those behaviors to create more area space. In order to do that, we need a basic scale and more efficiency tower. The more anchor of one tower, the better even space it is. So we choose the hexagon grid to be our basic unit. And then we were thinking how to expand this space. If they connect one by one, and the space is small and not area, so we developed a strategy to make a node between two near balloon strings and release them from the rover. Using this strategy, we can create a doom space with wrapping loops changes. We can also control the density of space openings. And we also did a physical test to prove our simulations. This is we manually set up 3 towers. Then we connect and cut the middle 3 strings. Then we connect the outside 2 connect strings so it flow up. Then we extended the balloon string to make an opening like an entrance. This is a big setup simulation to prove we can deliver a huge floating space for events. This is the sequence of how it's growing. This is a catalog of different growing strategy to fit different people activities. The geometry now is growing more horizontally, then we stimulated to make it growing more vertically. After UAVs wrapping a new tower, the rovers will extend more balloon strings, and the UAVs will wrapping the whole things. Then they create a huge high tower. This is the construction sequence. We are aiming to build a more floating space. Some of the rovers can extend the strings to let the whole structure up in the air to create an entrance. When two UAVs wrapping a tower, the red color means they are tracking the string they saw. The green color means they are close enough. They can rotate with the string. Then they will see the next string. So they react to the balloon string to finish the wrapping behavior. Then we add another behavior of UAVs. They react to the material they already deposited. The red dot is what they saw, and they try to close it. The green line is the material too close. They just keep distance with it. And the yellow blink is they try to jump. All the UAVs will have battery life, so they need to charge and refill. And with all these agents choreographed, they autonomously create a huge floating architecture with tons of details, texture consisted by interlock threads.
And this is the catalog of behaviors that we use for our design. For our project part, our research has been tested on a speculative project on the Burning Man Festival in the Nevada and Black Rock Desert, which is going to happen just 1 week before the Labor Day. This is the event for the self-expressive, self-reliance, and art and installation in a city scale. The activity inside will be like a cluster of movement, a cluster of people that change in over time. That's why we want to implement our airborne architecture that due to the 1 week and due to the various range of scales. Talk about the scale and activities. The activity mainly going to be like 4 or 5, 4 in the corner with the big pavilions, and the main event is the Burning Man himself waiting to burn down in the Saturdays. And for the scale of our architecture, our area construction system can adaptive cater to the different scale of event by construct more space when the space is needed, like in the picture, when there's more people, we will create a much larger space. And when the system running on, the size and the number structure would determine for the real-time relative to gathering more people to create a space. And at some point, they can create a tower-like structure, which gonna be like a signal to gather more people or signal to the rover itself to gather more structure to combine with him. So to start this event, the event will start with our construction by our station, which is, it can be a truck that carry our agent, UAV, and rovers. The rover and UAV gonna move out autonomously. Yes, autonomously, important. This guy gonna be where it's come from, and also where they recharge and refill their material. The rover will pop up the balloons as aerial scaffolding where the activity is, where the activity is. And the UAV will wrap our material to create a space in real time, respond to the activity itself. So as you can see, yeah, sorry for that technical. When one point moves, it's also moving all the space in the same time because our material and system are all dynamically and local. This is the final one that we test, the biggest one. We have 3 stations, 15 drones, and in total of 42 towers. Yeah, you can see the gradients of scale and the material itself. And after that, we lift it up to create a bigger space and canopy-like. So, wow, epic. In conclusion, our aerial force proposed temporal architecture temporal aerial architecture that facilitate a loose definition of architecture space in relation to human event, yet define lightweight material semi-enclosed space that are able to merge, bifurcate in real-time adaptive. We can also scale up, scale down, be dynamically create. And we achieve to develop bespoke lightweight material, aerial material development, flight, simulation, and demonstrate. And yeah, I want to announce something. This guy is actually outside right now. So it would be pleased if you just take a look before we take it out tonight. Thank you very much. Hello? Oh, yeah. So this guy, we can see the various scale of the geometry and the material inside. Also, you can see the space that's quite aerially constructed. These two guys are our construction sequence. As you can see, this first guy is the horizontally creative. And this one is, we test on we keep lifting the thread so we can achieve the geometry like a tower-like. And this set of guys are like let's say our prototype drones. You can see the red bit is like every time we develop on the red part. So like this guy, we develop the leg and the nozzle, and after that, we found out a better way to make it. And in the final one, we have these two guys as our agent, which this is our frost generator, and this guy actually the rover who's gonna power up the balloon. And yes, that's all. Thank you. The hologram, it's actually just a simulation sequence that we try to present. Yeah.
Hey, I'm not a critic, but I love the project so much. I have to say a few words. But first of all, I want to appropriate this for agent-based pragmatic semiology, because that's what it is. I mean, what I love about this is that you go out there and it demonstrates architecture. It doesn't have to do anything with shelter. It's pure communication, signaling, gathering, cajoling, and ordering event space, and that we do it today in a kind of dynamic and evolving fashion. But that's all this is, and I think it's striking and wonderful. And I think in the end you have a universe of agents, which is all of us, plus a series of architectural agents, and with different sense and intelligences and rule sets, but all coming together to create these communication events. So that's why it's within my paradigm, let's say.
Patrick,
just appropriate.
Adding to that, I mean, the one I would, you know, it can have a semiological dimension if you want, i.e. that it could be a kind of symbolic representation of the bringing together of people, et cetera, because we know to gather under the big spider nest in the desert. But it seems like also, for example, if we were to weave the smallest amount of copper into this machine, you would suddenly have an array in which the communication isn't an analog or a theory that we just gather and talk, but it would actually be the place where I could finally get decent 5 gigabyte wireless at Burning Man, which frankly is an issue these days. And the idea that it's got a materiality that does things rather than represent things, I think is staggering. You know, it is first of all, a network that would get you to the network, which is kind of bizarre. but that it could actually install itself in places other than these temporary event spaces, which obviously gives it a potential application that would be a bit at the scale of Buckminster Fuller's belief of working across the entire planet rather than in one particular moment. I think that's the other potential for it that's simply staggering. And by the way, it seems like once you've taken command of drone piloting as well as you have, and you're the only experts outside of, I think, Las Vegas, which is where all those American pilots are flying drones around the world, like, they need to find the four of you, because you can clearly, if you can knock together some software casually, the way you said, to control these things, it's a sort of staggering ability to position them in space. Why wouldn't you fold in, for example, the ability of these things to hang speakers? And so suddenly the deployment of sound is another part of the material. A light, God, I can't wait to see how you would light it, because you'd have a species of drone that would be sending different bandwidths, across an entire radio spectrum that would just be phenomenal. And it can be more than just a belief that it has to be the deployment of physical material, however beautiful it is. And it is totally beautiful. I mean, I completely agree with that side of Patrick's point.
But representation is doing stuff, so we need to give up that
It is, but it's not going to connect me back to the city I've left to go hang out in the desert for 3 days. I mean, the fact is, and if in spending time at these events, it has an experiential dimension that this thing can actually respond to in incredibly contemporary ways.
But architecture is awesome. I mean, what I think is what we see in this project is that being able to cut across so many domains with such a lucid proposal and being able to pull it off, and mastering Linux, mastering ROS, and being able to keep the focus, it's all inspiring. So you're really giving us a run for our money. It's really too difficult to take a step into this project. I think it's incredibly solid work. Maybe the most useful thing to say is that you have this cliche of that with great power comes great responsibility. Same thing with great creativity comes great responsibility. It can only go down from now, right? Is that how are you going to make sure that this happens, right? How are you going to stay focused? So you've loaded a great responsibility on your shoulders by making such an awesome project, and it's very commendable.
Can I just say, I did some teaching with Cedric Price years ago, and he always said that architecture is about theatre and entertainment too. I got to tell you, that is one of the best presentations I've seen for a long time. It was interesting. The project alone, I mean, it's just incredible. But then the way you did it with humour and entertainment, I thought it was just fantastic. Really, whether you actually meant it or not, but the point was, and I think, Archigram would be proud in the 21st century. Look at that. It's really an amazing piece of work. Honestly, you should be proud of yourselves. Fantastic piece of work.
You guys, you had me when you were spinning the floss. Like to be honest with you, the technology is amazing, but the sheer concept of we can make an infinite amount of rope so simply was really brilliant. I echo everybody else's thoughts.
I think what is interesting about it is the level of creativity. I mean, you talked about things and you put together things that don't usually go together that easily. I mean, it seems silly, and then suddenly 2 steps ahead, it wasn't silly anymore, and it was actually inventive and creative. I haven't been surprised by a project at this level in a long time, actually. And I'm willing to accept the fact it doesn't do anything but theater, actually, because of the creativity that you guys carried on, which I thought, okay, DRL is crazy. Is it crazy in a good way? That's a great ending to the day, if that's the ending of the day, I don't know. Also, I like the music. I know you took out the noise, the noise of the drones. I can imagine this being an incredible experience just to hear these thousands of drones moving, which is actually, they're quite noisy and they make a lot of wind, and there's something theatrical about them. And the theatricality, I think, is really what makes the spectacle happen. And I think what architects really want to do is create a spectacle, and you've done it with very ephemeral means. You don't need a big building, you actually need very small things, balloons and wire and almost sugar cane. It seems like this is an incredible project with very small, high achievement and only a big flair.
You mentioned aerial scaffolding sort of earlier in what you were saying, which sort of hints at something that's potentially temporary. And obviously, something that would be a Burning Man definitely is something that's temporary. I think that if you look at all of these different structures that you've come up with, putting them in tension with the balloons, the simple nature of that I think is brilliant. At the same time too, the structure begins to hint at something that could potentially go into compression. So I'm not sure if you explored at all sort of this model that you have here doesn't actually have any kind of suspension. It's actually a solid piece standing on its own. That could be something beautiful as well to think about. Getting rid of the balloons at some point, coming up with a material that can become rigid, especially in a Burning Man type situation where you're dealing with high winds, you're dealing with a lot of other forces on the structure that could be problematic. But there's something beautiful about that in sort of its essence, just standing free by itself, even devoid of the balloons or the scaffolding.
I'm also very fascinated by this work, and I especially like the way you worked on it, and that you really went into each detail. You really went deep into the drone technology, also software simulations, and the main or the most fascinating piece for me was that you really developed this lightweight material, which is, in my opinion, the key, actually, if you really want to build something aerial. And it has to be very, very much lightweight. And here you see just the ropes, but in real, it's not just a rope, it's foam, actually, in the air. And so, in my opinion, also, I think it's a brilliant project. Thanks a lot for this inspiring ideas.
Can I just ask a question about how you actually do your loadout? How do you pack this up and take it away?
From my side, I mean, the studio has really been dealing with the messy intersection between the technical side and the design side. And I think you guys have tackled this project incredibly well. What I see across the last 12 months on the project is a constantly attitude of we can, kind of like the Obama campaign. But it's like, we need a lightweight material, but there isn't one. We can make one. We need a strategy for scaffold. We can make one. There's a constant opportunistic attitude that I think really comes across, along with this kind of playfulness that you couldn't help but demonstrate in the presentation. I think these things are to your credit. What really interests me in the project is, first of all, the multifaceted nature of it, but secondly, it's a real demonstration as well of a non-linear construction process being a design process. And I think this comes across really when you show even the simple single tower, where it doesn't produce the same result if you wrap it from the top down or the bottom up. And you start to realize that the sequence in which you do these things has a huge implication on what you can make. And this starts to play its role, and then the entire design process goes through step by step how you can add another operation that somehow allows another thing to occur. And it couldn't occur unless it happened at exactly that time. If you were to change the sequence of actions or the operations themselves, you would get a very different result. And also, that's one aspect. And the other thing I would say is that the design process is very robust. I don't think your critique today would be any different if we had 3 less balloons on the table or 3 less towers. So what we have is a design methodology that is robust to variation, yet is guaranteed to produce something of the same characteristics every time, and that those are going to deliver the same kind of spatial relationships. And I think that's very interesting too.
I think it's in part because the kind of crowd sensibility, the material is a different kind of crowd, and the deployment not of a limited amount of material, but almost by design, too much stuff gets woven into this. The rendering maybe is the disappointment for their seven art connoisseurs who found it and are looking at this installation. And in a way, to take the crowd out is to miss the fact that this is aligning to this other idea of urbanism today and these temporary event spaces where massive numbers of people come together. The corporate modern Burning Man phenomenon is tens and tens of thousands of people coming together out on the desert. And there's an architecture that aligns with it. It's a really interesting kind of claim for this being a form of urbanism and not just a weekend event at the end of August every year out in Nevada. You know, Kumela would be a more extreme version, right? A Hindi city that every 12 years, and I think the 2013 version had 120 million people there, a temporary city built at a scale that dwarfs the city we know, could make a claim that this is a kind of urbanism and not just an event theater spectacle that's really even more demanding in terms of how it makes us rethink what architecture could be. And I would really speculate in the time you have now on its consequences back in that city you've left behind for a nice week up in the desert, which is going to be terrific, but is actually far more architectural than you're hinting at in this kind of image.
I think I kind of owe it to you because I was a pretty pain in the ass, I think, for the last year with you guys. So in my kind of self-declaration, like I really can commend you for play was a word that was kind of mentioned by Rob and concepts of Cedric Price and all of these other things I think are really valuable. But I think your approach to a serious play, like you guys always took this seriously, and I think that's what allowed us basically looking at candy floss as a serious material in the DRL as something that one could sort of explore. And I think that that's really, really valuable because in some way your unorthodox approach and your kind of open experimentation lends you to some really interesting discoveries. And I mean, following the stuff, I can say, like drones with chicken skewers flying around in the studio, stabbing electrical equipment. It's not always the smartest stuff, especially since some of them were metallic. But I think the value of all the experiments, like seeing those case studies that you've done up across the terrace, which we've had to negotiate quite a lot, seeing that world actually really offer a kind of real world testing experiments is, I think, fantastic. And I think that's a real demonstration on your part that you actually believe in the project. The simulation work is fantastic. And actually the idea that architecture could be lighter than air and all of these things are things that have been on for a while, but like I see your project in the spirit of, let's say, you know, Yves Klein's idea of an airborne architecture, just atmosphere. You could think about some of the experiments that Haus Rucker were doing, like when they moved from Europe to New York and made a food event. Like you can imagine that this thing could be an edible architecture, and that's how it could dissipate. You can imagine a lot of different versions if it is something that you feel is part of the whole conversation. I wouldn't relegate it to a tent. Like I think that the aspect of what you have and the sensibility of play is also not just to create a surface that stuff happens underneath, but I think closer to maybe some of the comments that Eleanor was making, this whole idea of the drone orchestra that's going to be happening around is as much a spectacle in itself without the need for Burning Man. Like I think Burning Man was as a kind of case scenario which you just have a large field to basically say that we could subdivide that and deploy it. But I think like a radically different kind of sensibility for space making and spectacle is completely inherent to the way that you've treated this. And the fact that this could be an installation that scales up to that scale, I mean, is I think a really interesting territory for you guys to look at. Because I think that that's a uniqueness that doesn't actually happen because you set out with that as an agenda, but it's something that you stumble on as you work through. And I think for that you should be really commended. So, thank you. Okay, so that was the concluding project for today, and tomorrow we have round 2. But at 6 o'clock today, we have our first keynote lecture. And so you guys can go to the bar and grab some drinks. We're gonna reorganize. Go outside and see the balloons of the kids, sorry. We're going to restructure the space here, and 6 o'clock allow people to come back in here for the lecture. So please join us for Adam Davis. Thank you.
mic back.
Okay, thanks everyone for joining us. For those who followed the DRL juries, today is day one of a 2-day event anyway, which we are sort of sharing some of the research of the students who've been working with us for the last 16 months. We've been working a lot on subjects around issues to do with behavior, exploring something that we've been calling behavioral complexity as a way to really sort of challenge certain orthodoxy within design research and to try to explore this kind of complex world between digital design, material fabrication and production, scenarios that are time-based and evolving, dealing with concepts that are very much latent and uncertain. And I think as part of this kind of evolving discourse that's happening within our program, between the different faculty members that are here, but also with a lot of the people that we invite, for us it's very important that this event is a very open and conversational, discursive kind of discussion on these subjects. As part of that, we have what we call a keynote lecture. We ask one of our critics, in this case 2 of our critics, basically if they can share some of their work, obviously with a belief from our side that a lot of the work that they're working on has very direct implications to some of the things that we're doing. And in a certain way, their knowledge and their workings in different industries and different backgrounds or disciplines actually helps us not only conceptualize what is a kind of evolving project, but also starts to share and disseminate and I think sort of forge relationships of like-minded people, which for me is a very important aspect of what design actually offers as a way of thinking, as a way of making, and as a way of thinking through living these kind of architectures and design disciplines. Tonight I am quite privileged to have Adam Davis give our first lecture. And Adam has a history which I'm sure that in the work of Tate Towers will be very familiar. It works in the domain of automation and staging and engineering and deals with the complexities of real-time performance driven kind of approaches to thinking about how people can experience directly, how performers can express through staging and deployment a kind of world within an experience that may be an hour, a couple of minutes, a couple of days. And I think the challenges of thinking about a lot of those real-time attributes, I think, are things that we are working on, and we feel quite interested in seeing Adam's approach and the work of Tate Towers. Tate Towers has a long-standing affiliation with Mark Fisher, who was a graduate from the AA, working on designs for the Rolling Stones and other things, and I'm sure Adam is going to show some of the stage designs and some of the theatrical setups that they've been working on. And so in a way, Adam, without knowing it, has always had a kind of relationship to the school and continues through a scholarship that they fund diploma students here, starting, I believe, this year. And so in a weird way, I'm going to keep this lecture short, at least in the introduction from my side, but to welcome Adam to the AA and to thank him for being generous after flying from the States and having a pretty long day as it is to kind of share, you know, and continue the kind of marathon. So with that, I'd love for the AA to warmly welcome Adam Davis.
Thank you. I want to thank Brett and Theo for trusting in me to come. I'm known for embarrassing people everywhere I go, so it's a bit rare. I'll start with just a brief, well, actually, let me start with, I love to shamelessly advertise anywhere we go because I am a brand ambassador, so you'll see that this is actually going to be a work of public advertisement.
The whole design starts with a concept.
there's one common thing. It's people who are passionate about what they do, and they're A players.
We look to our clients to push us as much as we're looking to push the industry.
Our clients are some of the best clients in the world. We're surrounded by the best people in the world at what they do. We're all out there to make the best show we can possibly make.
So let the shameless advertising begin. Today, the Tate Group encompasses lots of different brands and lots of skill sets. I was going to walk you guys through, kind of from the beginning, some of the projects and the way we think about things that has made us who we are. It is interesting that today what we've done, and it relates to architecture in a big way, is we've taken a skill set that started in rock and roll. And rock and roll, in many ways, we are the anonymous associate designer. We have a very creative skill set. And we've morphed into permanent installation. So for us, that's Ka in Vegas, or big installs in China, or maybe theaters here in London. That skill set's different because when we do a rock show, or what I would consider a portable show, we own and operate the equipment. So you can try new things, you can try crazy stuff. And we have the best people in the world using it, so we can get very quick feedback. When you're selling something, of course, you have to have a real engineering skill set and a real manufacturing skill set because you have to warranty it. And so over the years, we've also then developed a commissioning skill set to be able to deploy the equipment around the world. And today, our business is about 40% portable, the U2s and Rolling Stones of the world, or could be a corporate show from Microsoft, or the Apple launch, for example, when they recently launched the iPhone, which had 250 trucks load into the theater and more people streaming it than the Super Bowl. But 60% of the work is actually permanent. And we really see the future being in the kinetic architecture space. We think that public spaces are going to be enhanced with activity, interactivity. So kinetics, interactivity, and media. And I think it's necessary both to make the spaces transform, but also to drive traffic to it. Because I don't know if you guys have, does anybody have Amazon Prime here in the UK? Do you guys have that? Why would you ever go to a mall, right? And so you have to drive that traffic. So that, of course, hence why we have this renewed passion for architecture, and we've been spending a lot of time in that space, and are finding that surely it's pretty fascinating that the technology is just right now to deploy into that market. But I'll start with Lidditz. This is where we started. So the secret to the success is that we were in the middle of nowhere. Lidditz is a little town outside of Philadelphia filled with Amish. Ironically, that is what made us who we are today, because if you're in London, you think like, what is everybody in London doing? Or New York, what's everybody in New York doing? We're in the middle of nowhere, so for many years, because we didn't have the internet, we didn't know what anybody else was doing, and we just tried to exceed the expectations of the roadies that would come through and ourselves, because there was no entertainment. So today, it's turned into project-based manufacturing, in essence, or an engineering company, or logistics, or technology, and you'll see it's kind of hard to morph that. Basically, what do? We create the sandbox for artists. So we create the tools for artists to use and deploy. One of the unique things about where we live is it's amongst the Amish. So all my neighbors are Amish, and most of the community we live in is Amish, which does make it a little odd because, for example, when we were doing the London Olympics, I said to my Amish neighbor, I'll be gone for 2 weeks to do the Olympics, and he had no idea what I was talking about. So it's a very diverse skill set. So we started making decks, and our only form of feedback were the roadies. And when I say a deck, that's a platform, right? A staging platform, which is ironic when I show you the work we're doing now, because there was something really great. You could sleep at night making structure, because it's very hard to have structure fail. Now what we do is so critical to the performance that it can't fail. And so one of the things I think about our business is that it is mission critical. Everything we do has a very high cost of failure. If you can imagine a typical big show, if you've got, say, 30,000 people watching it and buying a ticket every night, you can't send them home, and the systems are critical to it. So we started making decks. Ironically, I'm the chief creative officer and one of the owners. Michael Tate, who founded the company, I think 38 years ago, made the extrusion deck, and it started with Michael Jackson moonwalking, because there were no smooth surfaces. So Michael, there's a famous story where he took Michael Jackson's shoes off and ran them through a router, put an 1/8-inch radius on it to make it smooth, and then came home and invented the extrusion deck. Over a period of time, we of course met the infamous Mark Fisher, and that is the tie-in. In the first show we did with Mark, I think was in 1989, if I'm not mistaken, which would have been Steel Wheels. And that changed us. We were a little company in the middle of cornfields, and Mark came and we became his craftsmen. That now has morphed to spectacle, these gigantic spectacle shows, and it sure was simpler back in the day. This is the London Olympics, where we turned the stadium into a video screen. So we deployed 78,000 individual pixels and then mapped them in 3D space. And that, of course, required, I think it was 347 kilometers of cable. So what we tend to do is really custom projects where we're developing the technology. It doesn't exist. In this case, engineering it custom and then going to China to have it manufactured, supervising that and deploying it. There's a funny transition in our company that started, ironically, this is for those of you that live here in London, the Super Bowl, where Janet Jackson had her breast revealed. I don't know, did that make the news? Did anybody hear about that here? Is that culture here? Because that was a big deal in America. Ironically, I'll tell you a funny story too, because we had this crazy machine in the middle of the stage, and it was a Rube Goldberg machine because it had to fit through a very small door, because we have 6 minutes to deploy the stage. And by the way, they spend $7 million on the grass for the Super Bowl, so it's all about deploying it without damaging the grass. The machine deployed, and there was a kabuki in the center of it that misfired. And I never forget, the show's over, and I left right, I'm on the field, I left right before the breast is revealed, and I go back to the trailer, and Mark Fisher was sitting there in the trailer, and I thought, and the kabuki didn't fire correctly, and I thought, oh God, this is, it's the worst thing. Kabuki, by the way, is pull a rope and the curtain falls, so to reveal her, for those of you that don't know theater terms. But I'll never forget going back to Mark and saying, Mark, this is horrible. We've totally failed. And by the time I got back there, our client had been fired, which is really unusual, right? You don't usually, you worry about yourself being fired. You don't think your client will. But of course, in the time I walked from the field of the thing, it had been revealed and they were fired. And so nobody ever noticed it. So, but there's a funny transition that happened here. We took that elevator when the show was over and we put it in a dumpster, my partner Winky and I we said to I can remember being there with the guy that was the dumpster driver saying, cut this thing up, we don't want to ever see it again. So we wanted to control our liability, because as a manufacturer in America, which is very litigious, if I sell something to Tyler and Tyler sells it to Carol and Carol sells it on, if a high school kid ends up hurting themselves on it, they sue you in America because you're responsible as a manufacturer. So we said, cut it up, and the guy ended up putting it on eBay. And so that was this kind of critical moment for us where we said, boy, we got to stop selling stuff. And today, the 60% of permanent installation is sales, but we now understand controlling liability. At that time, it was all rent, it was all portable, and so we stopped selling stuff and just started leasing it. And what's interesting there is the next thing that happens when you lease stuff is you end up with a warehouse full of stuff, and you have to put barcodes on it and categorize it. And we all of a sudden realized we make products, because we ended up with these buckets, like, oh, we make stairs, we make handrail. And the light bulb goes off because, of course, if you make products, why don't you have the same guy design the stairs every day and the same guy weld the stairs every day, and you can make it better. And so we set down a path of kind of making a Lego system of equipment. And so today, what I look at us doing every day, we have about probably 200 engineers that are designing stuff every day. They're creating new components of the Lego system. So a typical show that you see, 20% of that, what you see, will get recycled. But the 80% that is behind it is infrastructure that we're constantly building on and improving. And so you'll see, as I go through this, incremental improvement is a big portion of what we do. This is a Justin Timberlake show. It was out recently. And it's like, I don't know if you guys, I'm guessing this is not an audience that goes to see Justin Timberlake or similar shows, but there's a lot of complications here. That's a 150-foot long bridge that lifts up out of the audience, tracks 300 feet through the audience. No track in the floor, or we're blocking the fire aisle, which I love because that's a loophole, right? You're not allowed to block the fire aisle. So we've managed to get that entirely around the world. But in doing so, we sucked in LA first and then went to New York and then went to Chicago. And then by the time we got to Germany, we were able to say, well, these guys let us do it. The ceiling, the back wall, the floor, all projection mapped with 40 projectors. The stage surface itself is filled with hydraulic elevators, servo mechanics. There's winches all over it. So what's fascinating, though, is this, it's not what you see, but it's the choreography to get there. So we spend more time thinking about the process from it coming out of a truck, airplane, sea container, sub-assemblies, and put into place than we do what it actually looks like. That's the hard part. So for example, you're gonna see everything coming off in just the right time in these sub-assemblies, all engineered to undulate because the floor's not flat. You know, we're dumping, on a typical show like this, excuse me, the beer's, we might dump on this show, I don't have my numbers, well, I never have any of my numbers right. I exaggerate everything, so keep that in mind. But say we dump 25 trucks in the morning and 1 million pounds of equipment. We would start at 8 o'clock in the morning. By 2 in the afternoon, 6 hours later, we want to be show ready because we want to take the afternoon off and sleep because we then have to do a show and load out that night to go do it again. And so that human-centric engineering of how do I get it in place becomes super critical. For us, we worry more about the set carts and how I'm pulling the set carts out of the truck and touching them. If I have to take a piece out of a set cart and set it down before moving again, I've just wasted motion. Or if I can take a leg, our magnetic decking system, we can just pop a leg in and it clicks automatically. So to put it in, I go like this. To remove it, I go like that. There's no wasted effort. That times 1,000 and then times 100 cities, it starts to really add up. And so in this case, reliability is key. Labor savings and transportation savings is key. On a show like this, the transportation costs will be twice what it costs us to build the whole thing because they'll put it in 3 747s and fly it from place to place. So that, I think of it like a gigantic dance and a gigantic choreography. And it really is interesting that we put more effort into how the stagehands are going to touch it and feel it than what it actually looks like. What also is kind of crazy is the amount of detail that goes into it. So this is an interesting bridge that I'll show you again later for Taylor Swift that we just did. And I'm always fascinated by, for a show like this, we're really focusing with the artists that we're working with on what's the energy of the show, what's the Shakespearean story arc, you know, what's the evening gonna feel like? In this case, this bridge, we can dial in the energy of the room depending on where we put it. But it comes down to execution of 10 million parts. And in this case, it's single point failure all over the place. If this bridge has got her on the end of it, swinging through the audience, nothing can break. Everything is finite element analysis to make it work. That level of detail goes into even the wheels on the bottom of the set carts. So this is the set carts that you saw before. That's our plastic with our bearing, with our rig. This wheel, we can have 2 people push 2,500 pounds versus 4. When U2 went on their last tour, the first thing they did was threw everybody else's wheels away and replaced them with our wheels because they knew they'd go around the world. And in fact, it's a $75 wheel. It's, you know, most people would put a $35 wheel on the end of the cart. But that value is there because you now know it's reliable. You're not going to have to stop. And so there's a tremendous level of detail that most people wouldn't expect on these types of shows. This is that bridge. So what you see here in the bottom corner is an animation of a 3-point camera rig, and then the bridge itself. So what we've done, we do a lot of software. That's a big part of what we do. We're flying the camera, and we're moving the bridge, but we program her head. So the camera now, it's all object-based programming. So what we're able to do is now move the camera in 3D space, pitch, yaw, rotate, you know, but also focus, lock it in on her head, and that will also move the bridge to match. So what you get on IMAG is just her head stationary and the audience swirling around, but she's going all over the place as we do that. So make a little more sense with this. This is a rehearsal studio that we have in Lidditz at the main shop where we're testing it. And so in this case, this is probably, once again, don't trust any of my numbers, but 150 feet long. It can rotate from the center. It can counter tilt in either direction. The end of it can counter tilt, so she can stand on it. There's a revolve in either end, and the whole thing can track back and forth at about 300 feet, and it collapses to 4 feet. So now, this is maybe a 6-week project. So from concept to here it is go, that happens in a 6-week period of time, which just procuring the material in that period of time is insane. But we've literally engineered every single component, right? First off, society seems to value pop stars higher than they do regular people, right? Stagehands get hurt, you never hear about it. Audience members get hurt, it makes the news. You can imagine with Taylor. So this is, there's a lot of safety and single point failure that we really try to mitigate here. This is now, I think, show shots from the same show. By the way, the little town of Lidditz with all the Amish in it is made even more extraordinary by the fact that people like Taylor on this show was there for 6 weeks rehearsing the show. So you have to imagine that dichotomy, which is pretty unusual. What's even funnier is nobody cares. Like Gaga walks around town or Usher and nobody seems to care that they're there. So there's precision everywhere in what we do, and it's actually kind of counterintuitive as well, because if we take a Rolling Stone show like the Steel Wheels shot that was there before, let's just say that's 500 feet across, so you guys can convert that to metric yourselves. And if we were off a 64th of an inch on every deck, as we would call it, or stage platform, and say there's 120 of them, well, you're off inches at the end, and we can't be off that much. We have to be very, very precise in what we do. So over time, we've really transitioned to building things like a science. This is another kind of the next milestone in how we thought from, hey, we make products. Well, now it's how do I make stuff that can be put together very repeatable. So this is just an interesting transition. This is a video screen. We build a lot of video screens. This is a video screen that we developed probably 10 years ago now, but it's machined aluminum and it's a welded joint. Right, now we welded it in this case because we wanted to save the weight of not having all of the nuts and bolts. But the problem with welding, of course, is it shrinks and moves around. And so it's an art to put it together. One welder might put it together slightly different than another, and you don't necessarily know that it's exactly what you want. And so when I say we make things like a science, that's now transitioned to the pinned box joint. So this is, as simple as it is, that's a machined component that anybody can put a pin in. And in fact, what's great about it from our point of view is we can have anybody machine it as long as it hits the spec, and we can have anybody put the pin in as long as it hits the spec. And now I know it's exact, and I can send it anywhere in the world. And so over time, we've transitioned in how we manufacture things to really try to boil it down to a science. The other real transition for us was software. So the world of industrial automation still today is kind of dominated by these large companies, Allen Bradley, Siemens, Mitsubishi. It's what runs the elevators in the hotel or the baggage claim at the airport. And about 10 years ago, maybe 12 now, Scott Fisher, who founded FTSI, which is one of the brands we trade under now, thought, well, boy, that'll always be limiting. As long as I build something on top of somebody else's system, I'll be limited. And at that time in live event, that's what we were doing at Tate and everybody else was doing. You build a little GUI on top of an industrial automation system. So Scott set out to do it from scratch, which was literally insane at the time because it meant that the 99.9% that Siemens was doing, he wrote from scratch. Today, fast forward, and it's the core of everything that we do. So we've now got a software package. And I think today we literally have 40 people that continue to program on it every day. It's a network effect, building features into it. And that software, the way it works is it takes any input that we have a driver written for, it puts it into the system. The data is seamlessly available to all of the other data. With a series of rules or algorithms or artificial intelligence, we can manipulate any of that data, and then we can output it as anything we have a driver written for. So if we don't have a driver, we just write a new one. So what it means in real world is something like, this is Disney World of Color. We do a lot of theme park work, which is probably all NDA secret stuff. But for example, in this case, we listen to MANET, which is a native lighting language, because lighting rigs in the rock and roll world are gigantic kinetic rigs, right? A typical lighting rig, if you do the math, might have 20,000 axes. So lighting consoles over the years, without even knowing so, have been created as a programming environment for kinetics. So we listen to MANET natively. We listen to some wind sensors natively. We use the wind sensors to manipulate the MANET data and output it as, in this case, EtherCAT, which is a super fast industrial protocol. Now the fountains are always facing straight up, regardless of what the wind is. So that's just a really simplistic view of it, but real world applications, and I'll show you others. For example, we can take Maya. animate characters in it, then put a connects on somebody's body and use the connects to manipulate the metadata and then output it as KSI, which is KUKA language. So it's a very flexible, if you go back to the concept that we make a sandbox for artists, it's a very flexible programming tool. The other key to it is it's not happening in one centralized place, it's completely decentralized. So the network, it's built on top of the QNX operating system, which is what runs cars, nuclear power plants, planes. Very, very robust. The data immediately finds itself, and it shares itself, and it becomes redundant. And so it allows us on something like this to have literally hundreds of thousands of axes that are all talking to each other and sharing data just as they need. Because it's not uncommon that we're working at very, very high speeds. For example, we fly Tinkerbell at 70 feet a second. I don't know. Who can do the meter conversion? Can anybody convert on that? It's fast. It's from, so from here to the end of the room in half a second. So you've got to have, this isn't one winch working. We might have multiple hoists hooked up. Once again, doing object-based programming, everything has to be able to communicate very, very quickly. And of course, we're operating in an environment where you can't fail. It's got to be safe. This is another neat one using the software. This is, well, it's an opportunity to show you a girl in a bikini. But there's this is Disney Tokyo. Actually, I'll tell you another aside with this. This is Disney Tokyo Little Mermaid. And it's actually a pretty good indicator of how crazy our business is, because there was one day that, and this is a typical day around our world, but in one conference room we had Disney Tokyo, which means they have all the Florida guys there as well. In another conference room we had the Rolling Stones. And another one we had the Metropolitan Opera. They all show up wearing ties. And in another one we had the Hakkasan group that's building the largest nightclub in the world. And I brought them all together because it always cracks me up. Every one of them thinks what they're doing is the hardest thing on the planet. And so I love getting the guys together and saying, hey, Disney, like what you're doing is really tough, right? This has to run 28 times a day, 365 days a year for 10 years without failure. That's tough. Right? But the Hakkasan guys are building a $120 million nightclub in 6 months. That's tough too. And the Rolling Stones, they're going to go to 100 different cities around the world and have to be so flexible that they can make it up. And so I always love kind of mashing it together. And it illustrates all the diversity of markets that we're in and how the different skill sets build on themselves. So what we learn from building an animatronic statue that can run as much as it does, versus installing something in a construction site, those skill sets build on each other. This is that animatronic statue. We took a guy into a green screen room, put dots on him, did the motion capture, load that into Navigator software, and it outputs not only all of the motion profiles, but we're able to get the engineering data, because something like this is governed by material fatigue, right? It's not actually the forces, but it's at what point is the material going to start to fail because it's had so many actions and cycles. And of course, you can't have that when you have families around. Imagine the horror. Actually, can I do another aside? I was in a movie theater once with my wife. This is about 10 years ago. And my phone is just ringing and ringing and ringing and ringing and ringing. And finally, I leave the movie theater in the middle of the theater to go find out what's happening. And I hear the voicemail of Barney's bus caught on fire. And we had just built this bus for Barney the purple dinosaur. That might be before everybody's time. And I just had this visual of, oh my gosh, we just melted Barney in front of all these kids. But no, it was just a little shorted wire and smoke. But there's a high cost of failure. Spectacular race. So we're in a pretty funny market in that there's this spectacular race in live event, right? Everybody wants to top whatever everybody else has done and whatever they've done in the past. And so it creates this really funny situation. This is U2 360 from about, gosh, it's probably 7 or 8 years ago now. This was 205 tractor trailers of equipment leapfrogging around. The screen in the center, which we built, I've got a bunch of stories from this one. I'll start on the ground. So the stage in the middle is a double-decker stage. There's underneath that is a whole insulated and waterproof room filled with more electronic equipment than you can ever imagine. On the outside of it is an ellipse. But just imagine every day you're going into a different city. That ellipse could be plus or minus 2 feet by the time you get it in place. And then we have 2 bridges tracking around the ellipse over the audience. So they've got to be able to completely undulate. The screen above it is, I think, was about 100 tons, Hoberman designed structure that we built that as it opened up, it changed diameter at the top. And Neil is in the room, who would have done all the engineering on this. This is a funny story with it, which is the stage we acoustically coupled together with the bass. We got a 4 decibel increase by doing that, which is more than doubling the bass output, which is a pretty big deal. And we actually built a full mock-up in our shop. And actually, this is a funny Mark Fisher story. I have 2 funny stories with this. So we built a full mock-up of this in the shop, and it was late one night, and we finally turned it on. And we turned it on with the bass, and I thought, oh my, it isn't working, we're not thing. And within minutes, the police showed up. I thought, what are you guys doing? And we said, oh my God, we have 180 watts of bass, and we've acoustically coupled together. It's the coolest thing ever. And they said, well, you've just emptied all of the cupboards out of all of your neighbor's kitchen. And we told them, they said, can you turn it on one more time? Which I thought was just hilarious. And then Mark Fisher shows up the next day, and this was a classic Mark Fisher moment. I said, Mark, we figured this all out. Look at what we've done. He said, well, you know, Adam, at 40 hertz, the wavelength is 128 feet long. And he went into the entire acoustic science behind it. And that is one of the things that has always endeared me to him, in that I've always thought there is no difference between architecture, engineering, and manufacturing. It's one of the same. And Mark was one of those people that brought it all together. And it's really the way we try to think as well. You know, we're trying to merge the function of the piece, the engineering of the piece, the form of the piece, as well as what's the energy of the room going to be. So what's interesting about the spectacular race, to get back on subject, is that every day people come to us and challenge us to do something new. We know how to do A, B, C, and D. In my terminology, we might have already built the Lego bricks to do it, and they come and they challenge us hopefully to do E. Occasionally it's like we think it's E and it's F or G. You know, it's much harder than we think, and those are big learning curves. But every day what we try to do is make incremental improvements, just get a little bit better at whatever we're doing. So I call that prototype, prototype, prototype. This is a flying carpet we did for Disney Theatrical. They came to us and said, we want to put a carpet on the end of an arm. And we said, well, that'd be silly. You're going to see the arm. So we built a marionette rig in the air. So it's a 7-axis rig behind a curtain. The audience never sees it. And then hanging from it in each corner, rather than having a single string, we put 9 1mm Vectran strings and spun them at 1100 RPM. So they just disappear. The frame rate of the camera picks it up slightly, but in real life, you can't see it. Now in this picture, we haven't decorated the carpet yet. It looks like a carpet when we're done. So you end up with this just amazing magic illusion. They actually bring it out at house lights, in full house lights at the end of the show, and it gets a standing ovation. And we're now, of course, building 8 of them, which I love. But if you go back to incremental improvements in prototype, 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 so the day we came up with this, we would have had a motor, 2 pieces of plywood, and strings spinning around. We didn't go from 0 to this. We would have built this from 0 to 100 in, again, 6-8 weeks. But we would have done it step by step by step by step, proving ourselves out till we got it right. And there's a lot of little intricacies to get something like that right. What's funny is this now led to, this is something we did, again, with Mark Fisher, probably 5 years ago, where he said, and this was Mark's idea, he said, hey, I think I know how to do a hologram. You know, what if we render or shoot the person from, say, 30 different locations and make the image spin? Now, the challenge with this is, of course, you're moving a ton of air, and you got the spine that's always going to be black up the center. But after we did the Disney Aladdin carpet, we said, well, wait a minute, spinning strings disappear. What if we make those LED? This is just a first proof of concept digitally. We haven't actually tweaked it yet to get it to the point where it's really refined, but the concept's rather simple, right? Shaders on the LED sticks, spin them, and you end up with a 360-degree image, depending on where you look at it, and you can see right through it. So now we have to tweak it, like how long should the shaders be, how fast should we spin it, how many to get rid of the black lines, which is next. Then, of course, we got to figure out how to make it float magnetically, and then we really have something. But so it's incremental improvements. It's interesting as well. It's about the design circle. So it was when Theo was kind enough to come out that he, and everybody at our facility is tired of hearing me tell them this because I just have been drilling into it, but it really is about knowing what the goal is, right? And then building the right strategy. And so what we're often doing is looking at something and redefining the goal, because I find that often people don't have the right goal. And so in a sense, lateral thinking. So this is another example of incremental improvement. This is the nightclub that I referenced earlier for Hakkasan, where this was the first concept. Oh, let's go do a video ceiling. And we said, well, that's a great idea, but what if we make it truly kinetic? What if we can make it so you could dial in the energy of the room? In this case, it's a 40-foot diameter chandelier that moves at 8 feet a second. So I think that's 2.5 meters a second. I actually don't know the real number. Say 40 axes of motion. I'm making that up. I think it's got 6 winches so we can fly in scantily clad ladies with bottles of liquor to serve people. But what's interesting about it is you can completely dial in the energy of the room, right? You can take a gigantic space and close it down instantly and then make it take off. So the space can go from large and cavernous to completely intimate and then full of energy. And of course, from a promotional standpoint, every night when it happens, everybody takes out their phones and starts photographing it and pasting it on Instagram. And so it became a huge marketing ploy for the club. In another funny aside, I won't make you watch it again, even though, so I'm not ready to talk about this yet, but I'm going to tell you a story. So in a funny aside, we did that with Willie Williams, who's a rather famous lighting designer that lives here in London. And Willie, after we did it, he got an email saying, Mr. Williams, I represent a private client in Los Angeles that saw your chandelier at the Hakkasan nightclub and would like one for their home. Which time Willie responded, I just want to make sure we're on the same page. That was a 100 metric ton chandelier that cost $12 million. And they said, yes, our room is 12 feet tall, 30 feet by 12 feet. So we haven't, it's not a done deal, but I'm attempting to build the world's most expensive private chandelier at the moment. So Edward de Bono, lateral thinking. And this is going back to what's the goal, right? So this is something that I think we're really good at, and it's something that I think everybody I saw here today is really good at as well. And it's an honor to be in a room full of people that are good at it, because I find most of the world misses it, where it's really about pulling back and saying, what is the goal? And making sure you have the right goal. So for example, this is, I don't know if it's the best example, but this is a Bon Jovi video screen we built a few years ago, where it's a 400 square meter video screen. So that's a large video screen outdoors. And we want that thing to be rated for, say, 70 miles an hour of wind without destroying itself. And so traditionally, you would go build a gigantic aluminum structure behind that to deploy it and take that wind load. And of course, that's what we were headed to do. And then we said, wait a minute. We ended up coming up with a catenary system where we ran horizontal cables across. And those cables were spring-loaded to take the load. And now, of course, as you push on the screen, the cables stiffen the arch. And we were able to calculate the spring load, so they gave just the right amount to put the right amount of force into it. And so what ended up going from 3 trucks of aluminum, it turned into 7 aircraft cables. And so that's a really interesting one where nobody had ever done it, but we had to pull back and say, what are we trying to do? And we were able to solve the problem in a much simpler way. Okay, so the other thing about, this is that Bon Jovi show, and a random picture of a bunch of guys we work with a lot. But what's neat about the world of live event is we tend to work with the same teams over and over again. And there's trust that comes with that. And I think it's hard to, I think we often underestimate the value of that. But when you're working with the same group of people and you've been in the trenches together, you feel comfortable not knowing that you're going to get to the end result. We feel comfortable saying, hey, we're going to go down a path and let's see if we can get there. This is a show that was pretty complicated. And probably the 12th Bon Jovi show we've done. So it would have started in our room saying, what are we going to do to top the last one? And we went, well, we're really interested in interactivity, kinetics, and media integration. What can we do? And so we built a 3-dimensional video screen that's projection mapped in the back. This video tries to illustrate it. We've got, and once again, I'm lying about all the numbers, but say 50 columns in the back that are directly on top of 50 columns that are in the air. And the ones, 50 columns in the air that are directly on top of 50 columns on the ground. And what happens is the columns on the ground could go from, say, 2 meters all the way up to 50 feet. And columns in the air can go from 50 feet down to 2 meters. And what you end up with is a video screen that can open up in space, anywhere in space, and it's completely video mapped. So it's a 3-dimensional video screen that can open anywhere you want. We actually, with the same software I was talking about earlier, we we don't have any automation cues. What we do is we take video content in, we map an automation axis to a pixel, we use that automation axis to run the automation, and then we take its actual position to the media server. So because of gravity, acceleration, deceleration, now the video image is perfectly masked and synced with the motion. And so what you end up with, in essence, is video running automation and automation running the video. That's a loop we use all the time on these larger shows these days. We very rarely have automation cues. We'll often cue it from other engines and use the control system, which is doing the overall supervisor control for all of the different things, to synchronize it and just put the safety effects in place. This is, I was talking about incremental improvement. So this is a show, another show we did with Mark Fisher. This was Roger Waters' The Wall. Again, probably 6 years ago now. And so there was a lot of video on this show. To projection, at load-in, we've got, say, 12 20K projectors that have to get aligned and converged. So on this show, we put them in tubs, we put projectionists in the air, we lined them up to a grid, we had digital shutters that we built that kind of had serrated edges to get the black lines perfect and put them in place. 2 years later, when we were doing Bon Jovi, we had then advanced it to, okay, those tubs now were servo-controlled. We had a disto on them and a laser on them, and the shutters were now built into the projectors. So a guy on the ground, and it went from about an hour to, say, half an hour. The guy on the ground could now completely focus everything. And this one, we had, I think, 20 projectors in the front and 20 more in the back. And just 2 years later, we're at Justin, we've now built pulse width mod LEDs into the whole set, each one with its own individual identifier. We look at the whole set with a few infrared cameras, and we could automatically converge and focus the projectors, and it took about 30 seconds when you hit a button. And so it's interesting, that's all project-based innovation, and there's all, the drive behind it is how do we save labor. It happens very, very quickly. I don't actually know what this is. This is a exciting video of different shows. So I've probably to a fault kind of shown you guys a bunch of shows or projects that are more on the portable side of things, where this is an audience that I think I want to be bragging to about the permanent stuff we do. Some of that is in here. This is the Olympics. Some of the largest shows we're building right now are actually shipping into China and getting installed in China, or in Vegas, you've got, for example, Ka, or cruise ship work. Cruise ships are tough, of course, because the ship isn't torsionally stiff and it flexes. So everything you build has to be able to take that loading, and there's no such thing as putting something in tension, right? Because at any moment, a big wave can come and the ship can slap. And so then on top of it, so now anything, you imagine the forces and calculating and figuring that out, but then it's out to sea, so there is no servicing it. So it's gotta be incredibly reliable as it goes. Okay, this is kind of cool. This is a project we just did. Go back to prototype. This is the second prototype. The first one we did was an air beam. We just said, hey, we think we can use high pressure air as a support structure. So we took an air beam, built I wish I had a picture of it, but built an arch. We could hang a car from it. It's a nylon polyurethane coated with stress bands in it, inflate it to about 60 PSI. And it's interesting what happens, right? The air becomes the compression member. Everything's in tension. And so it has a great failure mode, because as long as you're overcoming that tension, everything holds itself up. But if not, it just buckles a little bit, versus metal, which just fatigues. And so that was the first, this is a picture of the second prototype, but what I just described is the first prototype. This is the second one, where we just said, hey, what if we make it triple redundant? And we built maybe a 30-foot tall long beam to test it. Now, because it required custom weaving of all the fabric to get that into one cell. And the final piece then was a 5-story tall structure out of these air beams that were woven together. This is a test and a setup in that same facility. And what we ended up with was a gigantic, I think there's a movie. Oh yeah, okay. This is, of course, the island of Pandora, or the world of Pandora from Avatar. Has anybody seen the movie Avatar? We just built the prequel to it, which if you're us, that's like your worst nightmare, because there's no straight lines.